to introduce the colloquium speaker of today and my PhD advisor, Miranda, who will tell us everything about the love story between integrable systems and group actions.
Thanks a lot, Anastasia, for this generous introduction. And thanks a lot to Nikita and to Beatriz for this wonderful, I'm enjoying a lot this junior meeting. And well, this is online, this is on YouTube. And I must say that the senior must learn a lot from the junior in that respect. I mean, it's like absolutely great the way you are handling this. So I hope to be up to the level of the conference. This is really like a colloquium style, so everything is basic, just sit and enjoy, and I don't know, feel free to ask. Well, I don't know if you can ask because you are all muted, but well, you can, I don't know, if I have a slide will tell me if you have questions or you can post them here. So my idea is to give general ideas about group actions and Poisson manifolds, and most of the things I'll be explaining is very classical literature. So the plan of the talk is that whenever there is a love scene between groups and Poisson structures, the word love, like in this file, like in this slide, will appear. So because you are away, I don't know how, if you like it or not, feel free to send me these little hearts that you have as reaction whenever you see the love, or if I didn't put the love, if you think love should be there. Good, Anastasia. Okay, so that's the schedule. I may jump things, right? So who are the usual suspects? Well, the usual suspects of my story, well, we could say it's Liouville, it's Poisson, it's Mineur, it's Lee, it's Einstein, it's Noether. These are the usual suspects. But if you see, I decided to sneak in some of my young junior Poisson collaborators, Anna Kissenhofer, Jeff Scott, Robert Cardona. We have here Arnau Planas, who is not connected, but he's working hard for his thesis. Anastasia Matveeva, who is organizing this great event. Narita Pires, Pau Mir, well, Camille Laurent, well, who is not that young, but it's okay. So I decided to add a little bit of spice to the usual suspects. So I'm going to try to explain in very basic terms the relation between symmetries and the Poisson bracket and what we can do with that. But it's going to be really basic. So I'm going to start with Noether, with Emmy Noether, who is here. She is highlighted. And well, Noether brought us a big idea, which is called as Noether's principle, which I'm going to vaguely declare as conserved quantities give rise to symmetries and physical systems that can be encoded as group actions on this manifold. This is a simple pendulum. And here, well, the conserved quantity can be thought to be the energy of your system. Okay. Well, I have here the chat. Okay. Yeah, I mean, Noether, maybe she's in a meeting. You'll know. I'm replying to Han Chen. Jeff is there too. Okay, hi Jeff. Great to see, to know that you are there. And yeah, you'll see. Keep on the last slide. Where is Emma Noether? Maybe she's here. We'll see. Who are the usual suspects? Okay, so the total energy of the system, it's here in the simple pendulum. It's the conserved quantity. Okay, so okay, then very basically, and as a motivation, I'm just giving general ideas. Here we have Hamilton's equation, and we know that the existence of symmetries in differential equations allows us to reduce the degrees of freedom. So now we want this kind of general or mantra idea or general idea that symmetries are useful to reduce degrees of freedom in differential equations. We really want to state this somehow properly using the language of symplectic geometry. So to start with, everybody here knows that Hamilton's equation just corresponds to the equations of the flow of a Hamiltonian vector field, okay, associated to H, which is usually the total energy of the system. And this is exactly the equations of the flow when I consider the Darboux coordinate indeed, okay, the Darboux coordinates, which are this one. And more generally, of course, one can observe that this omega, it's the differential of the Liouville one form, therefore it's closed. Also, it's non-degenerate. This is why this equation always has a solution, a unique solution. And more generally, the geometrical structure behind this formula is classically known as the symplectic form. Indeed, Poisson was the first one who introduced the Poisson bracket, and he did it for symplectic forms. So now it's time to talk about Poisson. Poisson highlighted here in our list of usual suspects. And this is the extract from his Mémoire de l'analyse sur la variation des constantes arbitraires dans les questions de mécanique, which is from 1809, okay? And here is the first place in this piece where we can really find the formula of the Poisson bracket. A big deceiving, though, that he doesn't use the standard formula, he uses just the standard brackets, but this refers to the Poisson bracket with respect to the standard structure. And this, which nowadays looks very simple to us, looks trivial, in that moment was important because of this idea of trying to solve differential equations. So as a first example, of course, and this is the example that Poisson initially had in mind, is the case of symplectic manifolds. We may now revisit Noether's principle, which we saw indeed this morning in Jana's talk, in Jana Wieniewska talk. She already talked about Noether's principle when she was restricting to the Hamiltonian equal to constant, and she was looking at the Hamiltonian equations on the restriction on an hypersurface. And here we may think of Noether's principle just as nowadays it's very simple. You have a function and you have the Hamiltonian of this function. And of course, this is just the differential of f applied to the Hamiltonian vector field. Therefore, this is the symplectic form applied to the Hamiltonian vector field. And because this is because this is skew symmetric, then you get 0. So Noether's principle is tautological for us. And what about the language of Poisson geometry? Well, the Poisson bracket for a general symplectic form, not for just for the one that Poisson was mentioning in the previous slide, is just given by applying the symplectic form to the pair of Hamiltonian vector fields. And in this language, Noether's principle just reads, is tautological again, because it reads as the first property we ask for a bracket to be Poisson, which is a skew symmetry. Okay. Therefore, if I take the Poisson bracket of a function with itself, it's going to be 0. So let's say Noether's principle with this new language is tautological. But when it was first formulated, it was a completely new idea. Now it's tautological with the language of Poisson geometry. And here just a picture, and the idea of the picture is that the flow of the Hamiltonian, here I have rotation on a sphere, and then the moment map is just the height of the sphere, and the rotation of the sphere, the orbits, okay, or if you want the orbits, the flow of the Hamiltonian vector field are just the parallel the parallels of the sphere, okay? And exactly this coincides with this idea of preservation of energy. And this nice idea of preservation of energy allows us to reduce degrees of freedom, but we need to go a little bit farther. So we need new tools. Let me look at example 2 of Poisson, very simple Poisson structure, which we have been seeing all these days. For instance, the Gelfand-Sidlin system is an example of integrable system on the dual of a Lie algebra. So if I consider a Lie algebra, okay, and here I take just the Lie algebra of matrices. I just take a very simple example, the Lie algebra of the SO3 of the special orthogonal group in dimension 3, okay, and here I take a basis, okay, and I just take the brackets, the Lie brackets, okay, then I can automatically transform with a magic stick these Lie brackets into Poisson brackets just by changing the notation. And more than changing the notation, I can think that I work in the dual of the Lie algebra, okay, and I just change the Lie brackets with the Poisson brackets. And of course, this is going to satisfy Jacobi identity. Why? Well, because the initial vector fields that we took satisfy this identity. Because we know that if we take the commutator of matrices, it satisfies Jacobi identity. And by duality, the Jacobi identity is also satisfied in the case of the dual of a Lie algebra. And we know this is one of the basic examples. So symplectic manifolds and the dual of Lie algebras are one of the basic examples of Poisson structures. However, Poisson structure, as you know, all you know, can be absolutely much more complicated. In a particular case in which, well, here I was a little bit, well, in terms of language, let me, before I wanted to talk about the more general case, but before that, in terms of language, we can use the bracket. Nowadays, the language which is more used is that of bivector fields. And to write this bracket as a bivector field, we write it like this. And to work with bivector fields has some advantages. That is, thing that you can compute much more quickly. And in particular, in this particular case, you can check that the function x1 squared, x2 squared plus x3 squared, which is the distance to the origin, is indeed a first integral. Indeed, for all the elements. So any function, this would never happen on a symplectic manifold, but any function, okay, has a zero bracket with this function. What does this mean? This means that when we take f equal to constant, we have these concentric spheres, and this coincides precisely with the symplectic foliation of this Poisson manifold. So we can think that symplectic manifolds are a fundamental tool in Poisson geometry, but as you probably know all by that, it's very hard indeed to prove most of the theorems in Poisson geometry, because you cannot just think, because this is true for symplectic manifolds, this is going to work for Poisson manifolds, because the symplectic foliation of a Poisson structure can be really very complicated and usually has singularities. And these singularities, or jump of dimension of the symplectic leaves, is part of the beauty of Poisson geometry. And this is what makes it so different from the symplectic wall. Okay. So in a way, we have this, just to put things in a very easy context, we know how the bracket works for the dual of Lie algebras and how it works for symplectic manifolds. And therefore, we can think that locally, we could initially think that this is enough to describe the bracket in general. Okay, why? Because we have this result of Alan-Weinstein, which tell us that the best we can do about finding a kind of Darboux theorem for Poisson manifolds is a theorem due to Alan-Weinstein, which is a theorem of 83. Most of you were not born there, but some of us were born by then. And it's fairly recent to think like, oh, this was not known before. No, this was not known before. So before Alan-Weinstein, nobody knew that a general Poisson structure could locally be written this way. Okay, so the expression tells you in a geometrical way, well, this is an expression, this is an analytical expression, but if we want to describe this geometrically, we would say that locally we have a product of symplectic manifold with a Poisson structure which vanishes at the point. Can we say that this is the same as a product of a symplectic manifold of example 1 and a Lie algebra of example 2? Well, this is not necessarily true, because we may have Poisson structures which are not linearizable. It means we cannot find a diffeomorphism taking our Poisson structure to a linear one. And indeed, it's very interesting the study of situations in which this can be done. And there are some recent works by Ionut Marcoux and Marius Kreinig concerning these kind of ideas, which are really beautiful. And we can think, like, just in a naive way, just to present things very easily, that for linearizable transverse Poisson structures, example 1 and 2 are enough, and they are the building blocks of the theory. Now let's go on with our bingo. And now we have Sofia Kovalevskaya. Okay, time to talk about Sofia. And maybe time to talk finally about what is the definition of integrable system, which most of you know. I imagine that all of you, but this is a colloquium, so I'm going to assume nobody knows anything. Sofia Kovalevskaya is very well known for many things, but one of the things she's known from is from the spinning top, because she looked at the solutions of the equations of the spinning top. okay, which is the rigid body. It's not so funny to say it's the rigid body. It's funnier to say we are talking about the spinning top. And she proved integrability. So she gave explicit solution for a certain relation among the inertia axes, okay? One of the axes has to be double to the other axis, and two of the axes have to be equal. Then it's integral. This is what she proved, and this is why she's in this picture, okay? Because at the beginning, integrability was found like, I mean, you have some equations and try to solve them, right? Look the best way to solve them. And well, the message is if you have additional friends, enough information, which is additional constants of motion, one constant of motion is going to be the total energy of your system. This is going to be one of the constants of motion. But if you have more, if you have enough of them, then you can integrate them. Okay, and this idea that is often used in the actual integration, as I will explain later on in the case of the two-body problem, indeed, while you are trying to solve this differential equation, you find the first integrals. So what is the definition of integrable system? An integrable system for us is going to be a set of m functions. I'm going to start with the symplectic, with the case of symplectic manifolds. I'm not going to go very far away from the symplectic case. I'll slip towards the end of my talk into a little bit the Poisson world, more general Poisson. But there's a lot of already a lot of beautiful things in the symplectic world which are still not understood. So let me stay there for a while. So if my manifold has dimension 2n, then it means that I need to have n functions. So as much as half of the dimension of my manifold, and I need to impose that they Poisson commute. So they commute with respect to the Poisson bracket, all of them, among all of them. And I'm going to assume that they are functionally generically independent. This means that if I compute the wedge of the differential of f1 fn, this is different from 0, at least on a dense set, okay? Because if your manifold is compact, you are not going to be able to assume this condition for all points. But on a dense set, you can assume that they are that the differentials are independent. And usually you call the set of functions, you collect them as a mapping from your symplectic manifold to Rn, and you call this the moment map. Okay. The notation of moment map is also used in Hamiltonian systems. So we are going to, one could think, oh, these people of integrable systems are using the language of the people of Hamiltonian actions. How they there? Well, we're going to see that indeed, given any integrable system, we have a moment map, a Hamiltonian action associated to it. But this Hamiltonian action is often to impose that this is global, it's too much. We're going to see that we have such an action in a neighborhood of famous torus, which are called the Liouville tori. And this explains a little bit why I put this picture here, because Liouville tori are, well, if you, this is, I'm going to reveal it in a few slides, so I reveal it now. We're going to see that when you have an integrable system, if the leaves, or if the fibers of your system are compact, they are tori. And then there are these people working in dynamical systems who, of course, start with something which is integrable and need to perturb it. When you perturb an integrable system, you're away, you are lost. You are no longer integrable in general. But there is a theorem due to Kolmogorov, Arnold, and Moser, which tells you that there are a lot of these tori that survive. And these are the tori in this picture here. This is the KAM theorem. So as a first step to KAM theory, let's say a building block of perturbation theory is to understand first integrable systems. That's why they are so important. So on the other hand, it's not a surprise that it's known that if you have a group action, and forget now about symplectic manifolds, you have a manifold, a compact manifold, and you have a compact group which acts on this manifold. It's known, thanks to Richard Palais, who is in the list in the first slide, that if you have two actions of the same group, okay, if they are close, they are equivalent. And this theorem indeed is connected to the KAM theorem. So we may visualize the KM theorem under the eyes of a geometer using group actions. I'll mention some of these later on. Okay, so these are in this slide, we have the main ingredients of the day. We have an integrable system. There is a picture of Kovalevskaya. We have spinning, so we can play with our spinning tops if we get bored. We have Hamilton's equations. We have moment maps. Let's go on. Let's go on with an example. Let me start. I'm going to give a couple of examples of integrable system, which are classical. The first one is going to be, I could say, the harmonic oscillator. I'm going to make it a little bit more complicated. I'm going to say to take two simple harmonic oscillators, and I'm going to couple them. Each harmonic oscillator lives in dimension 2. So when I couple them, I'm living in dimension 4. So the phase space is as a cotangent bundle of R2. This is non-compact, and the total energy is the sum of, here I use the standard notation of position and momenta, and this is the kinetic plus potential energy if you compute this, because I use the equations, Newton's equations, and I'm killing masses here because I'm a mathematician, so masses are 1. I unify everything. Okay, if I take h equal to constant, I want to play M in ether, and I take h equal to constant, what I get is a sphere of dimension 3. Okay, and a sphere of dimension 3 is symmetric by rotations. Okay, in other words, just by knowing how the hypersurface is, I know I have another invariant there, which is the angular momentum. So I have the total energy, the angular momentum. I have two first integrals. If they Poisson commute and dimension 4, I win. This is an integrable system. Well, it's pretty easy to check that they Poisson commute. This is the angular momentum, the standard angular momentum that you learn in physics. And with respect to this symplectic form, this is the Hamiltonian. I have computed for you the Hamiltonian vector field. And now just apply this Hamiltonian vector field to H, which is the equivalent to computing the bracket, the Poisson bracket. And look, it's an easy computation. I get cancellations, it's 0. Therefore, they commute. This is the first example. Let me look for another example, more geometrical or more intriguing, which is that of holomorphic functions on a complex plane. So I take a function from C2 to C, which I assume holomorphic. So it's going to have a real and imaginary part, which here I call G and H, which, because it's holomorphic, they need to satisfy the Cauchy-Riemann equations. Okay, so I impose the Cauchy-Riemann equations there. These are the equations we learned second year or first year of the undergraduate. And the funny thing is that we can look at these equations as the following. We can look at these equations here, which you may think that this is equating the coefficients of two Hamiltonian vector fields. That's what these Hamilton equations look like to me. Okay, this is the first coefficient of a Hamiltonian vector field, and this is the first coefficient of another Hamiltonian vector field, and they are the same. And they are Hamiltonian vector fields with respect to two different Poisson structures. More convenient, we can prove that this is the same as saying the Hamiltonian vector field of G coincides with respect to the Hamiltonian vector field of H, but with respect to two different Poisson structures, which are nothing but the real and imaginary part, the real and imaginary part of the symplectic form I'm considering, which is this one, in complex coordinates. Okay, so if I compute this Z1 is x1 plus iy1, if I compute real and imaginary, then I get two Poisson structures, which indeed are compatible as Poisson structures. So this is more than just a Hamiltonian system. This is a bi-Hamiltonian system. Okay, we can now check that not only this equality holds, but from this equation here, J and H define integrable system for both Poisson structures, which are symplectic in this case, which is omega 0 and omega 1. This is another example. This is a nice example, which indeed I found. I didn't know about this example as integral. I never thought that this was an example of integrable system. This is in the book of Paul Van Aken, in one of the many books of Paul Van Aken. one of the first books of Paul Van Aken as integrable systems. So now here comes the main theorem, the main dish, which is the main theorem of the theory, which is the description of, well, I have an integrable system. I want to know, if I'm a geometer, how, for instance, how does this integrable system looks like? There is a question here. Let me see if I can look at the chat. Ah, it's Nikita, thank you. Yeah, I knew you would like that example. That's why I put it. Okay, so as geometers, what do we want to know? We want to know how does an integrable system look like, right? What does it mean how it look like? Well, first, topologically, for instance, how are the fibers? And secondly, can you tell me how does the symplectic structure look like? Locally, any symplectic structure, Darboux theorem tells me that locally in a neighborhood of a point, all of them are equivalent. But now I want to know more. Are they globally equivalent? This is too much. But are they equivalent in the neighborhood of a compact torus, of a compact fiber? That's the question. So, well, this is the theorem that I call Liouville-Miner null, and in the literature, in 90% of the books, is called Arnold-Liouville. It's the same theorem, but I'm going to stress why I put Miner there. So my locally alone, well, first thing is that the level sets of an integrable system are Liouville-Tori. Indeed, it was not Liouville who proved this. Liouville just proved that when you look at the fibers, so F1, Fn equal to constant, these are invariants by the system. But he didn't prove that it's a tori. This came later on, but they are called Liouville-Tori. So the first thing, as a geometer, these fibers are just torus. That's nice to know. These are Lagrangian torus, of course. Okay, because the condition that the brackets are 0 is going to tell me that they are Lagrangian. Okay, then so the theorem tells me that in a neighborhood of a torus, the symplectic form is of the Darboux type, where I can write the symplectic form in these terms, as you see here on the screen, okay, as the sum of the dp, d thetas, and the p is called the action coordinates, and the thetas are the angle coordinates on these torus. So indeed, it tells me that a neighborhood of the torus is just as a cotangent bundle of the torus, indeed, with the canonical structure of a cotangent bundle. Okay, I could think of these terms. The canonical structure of a cotangent bundle is a differential of a Liouville form, which is of this sort. Okay, that's the first thing. And the second thing is that, okay, now I give you an integrable system and you tell me that there are some other coordinates. What is the relation between the action coordinates and this integrable system? Well, in a neighborhood of a regular point, I may assume that all the functions are functions of the P. Okay, and here I'm assuming that I'm in a neighborhood of a regular point. And this is, in other words, I could say that the level sets of the fibration, my initial fibration given by the integrable system and the action functionals are exactly the same. That's the theorem. Okay, this theorem, therefore, is telling me that these action angle coordinates exist. They are not local in a point, but in a neighborhood of these torus. A natural question is, can I extend this globally? No, this is asking too much. And indeed, the proof of this theorem I'm going to describe, I learned it from Doistermat, okay, from his paper, where he discusses when you can extend local, what are the obstructions to global extensions. One of the obstructions is given by monodromy and the Chern class of the fibration given by this moment map. Okay, let's go on. So if I had to write a picture, this would be the picture. That's a picture by Jeff Scott. Thank you for this nice picture, Jeff. You're going to recognize many, many pictures in this talk that are going to sound familiar to you. I learned a lot from Jeff. So one is this. These are a collection of Liouville-Tori, and in action angle coordinates, well, this is telling me that the fibers are just given by pi equal to constant, and that the symplectic form is simple. That's the only thing I need to remember. Okay, and okay, let's go on. Who's next in our bingo? Miner. Why did I talk about Miner? Who cares about Miner? I care about Miner and other people care about Miner, but who was Miner? If you look in Wikipedia, there is interesting things about Miner. Well, first, he was an astronomer. He was a mathematician, but he was very active in the French resistance against the Nazi system. So he has a very, very interesting story. When I was young, this is a long time ago, of course, I went as a postdoc to Toulouse. And then I had always learned that for me, this was Arnold-Liouville theorem. And then out of the sudden, soon tell me, no, the formula, the action formula, it's already in a paper of Miner. I said, really? Yeah, I went and check it. This is a paper in a Cologne Polytechnique. And if you look at the paper, it's written in a as an astronomer, indeed, but you find the action formulas. The action formulas classically are just given by integration of the Liouville one form along the cycle in a Liouville torus. So this that you find in the book of Arnold Mechanical, where we all learn this theorem, indeed you can find it already in this paper by Miner. So then I decided like to jump on this Frenchy turn of adding Miner to the list of authors of this theorem. Indeed, I was not alone. I mean, then Sam Munok. So when I was a postdoc, this is one of the interesting things I learned. So that Miner had a major role in this business. Okay, so that's why his name is there. Who's next? Let's talk about Hans Duistermatt. And well, Hans Duistermatt, what I'm going to do is, indeed, he has an approved, he has many nice papers, but the one I'm going to talk about is a paper called On Global Action Angle Coordinates. And indeed, this paper gets super complicated because he describes abstractions to these global action angle coordinates. But a beautiful thing that I found in this paper, and I didn't find in the other sources, is it's the nice idea of how Hamiltonian actions, using this idea of Hamiltonian action by Toric, you can really prove the action angle coordinates. So I'm going to start recalling what is a Hamiltonian action and what is a moment map. By now, everybody in the room knows this, but let me recall it. It's always good to recall things. So if I get any compactly group, I assume that it acts symplectically, so it preserves a symplectic form. We say that it's Hamiltonian. Okay, if when I consider the fundamental vector fields, okay, these are Hamiltonian vector fields, but they are Hamiltonian vector fields in a collective way. In the way that, the way to describe it, the first time, this is what I told to my students, the first time you see this definition, you need to go through it twice, 3 times, like it's sort of hard. You need to think about it. You just, what are you asking for? Well, you are asking for the fundamental vector fields to be Hamiltonian, but you are asking to the fact that we need to have a kind of collective Hamiltonian, which is this mu, which is a mapping from your symplectic manifold to the dual of the Lie algebra. Now, because we are all very clever by now, we could, because we are at the end of the workshop, we could say that we could just ask that this mu is a Poisson map. Indeed, this is true with the Poisson structure on the dual of the Lie algebra. That's a way to go. We could say, well, require that this is a Poisson map. But, well, I'm going to act classically now because, well, in the Poisson case, this is a way to go. And we require that this is equivariant. We need this condition of equivariance. Well, if you look at some books, you drop this condition and then you call it weakly equivariant, strongly equivariant. Let's ask for it today to be equivariant map, which in the case of the torus doesn't affect because it comes almost for free, okay? Which is the case we are going essentially to consider today. So, well, if we have such a map, equivariant, just that each component of the map, so this mu x, let's say it's the component of the map, mu x is the contraction of mu with the vector. So this is like just thinking as a component of the map, okay? Just that each component is a Hamiltonian function for the fundamental vector field generated by this x. X is a vector in G, therefore it generates a fundamental vector field on the manifold, and now you contract this, okay? And you get a Hamiltonian function. And this Hamiltonian function is a component of the moment map mu. And the way to say component when you have a general Lie group is to do it in such a complicated way. Okay, And moment maps and reduction provide effective tools to study symmetries. And there are a couple of pictures, very important people to me in the bingo that I will not have time today to describe the many things they did or nothing. I'm not going to be able to describe because I don't have time, but it's Francis Kirwan and Lisa Jeffrey who did a lot of things concerning the symplectic quotients for general groups. But I'm going to focus on the torus case today. So they are on the bingo, but I didn't have time to put them on, I mean, time in terms of time to do this talk and not killing everyone with my slides and get you there and really talk about this seriously. Okay, so now it's time for love. Okay, thank you, Nikita and Anastasia. So this is, and what is the love here? What is the connection? What is the love affair in this slide between integrable systems and group actions? Is this proof? This is the proof by Doisterman. So Doisterman proof, well, first, the topology of the vibration is very simple. Because if you have a vibration in a neighborhood of a compact manifold, then you can prove that it's a trivial vibration using Ehresmann connection. This is something that I didn't learn from this paper, but he proved very nicely that these fibers are tori, but proving that there exists a group action. Okay, so the group action he considered is what is called the joint flow, which is take the Hamiltonian vector field of, well, here this R and this R and S, this is done for general Poisson, but in our case R and S are equal to n, and the dimension of the manifold is 2n. Okay, so I take, what are these guys here? These are the time tier flow of the Hamiltonian vector field of the function su pi. Okay, so if I have f su pi, this is the timer flow. Okay, so this is what this is doing, is to walk on your manifold by flowing around the vector fields of your integrable system. And what he proves is, well, to prove that this is an RS action is an interesting thing, that you have an action of R. But what is more interesting is to see, indeed, that could be an exercise, okay? That to prove that this describes a group action, well, you need, because why can I assume that the flow is defined for all t? Well, because you're assuming that you're in a neighborhood of a compact manifold, therefore it's complete, this flow, okay? So I don't need to assume that it's complete, I get it for free. And well, and the interesting thing is that you can, well, that there is I mean, your manifold is compact and you take these flows and there are some periods, okay? So there are some periods concerning this flow. So this action, I may go after a while to the initial point, okay? So the key point in the proof provided by Doisterman is that he proved, just using the inverse function theorem, or call it as you want, implicit theorem, he proved that you can uniformize these periods. And uniformizing these periods means that if I have a point and it has one period and it has another point and it has another period, I can find a continuous function. So by uniformizing the period, what he proved is that this action induces the action of a torus. And that's the key contribution by Doisterman, which I didn't find elsewhere. A posteriori, yes, I found it elsewhere, but at that moment, I didn't find. So I found this beautiful, beautiful idea. And well, what he did is, well, to prove that this action is symplectic first. And then, because omega, we are in a neighborhood of a Lagrangian compact torus, we know that the class of omega is 0, the rank homology class. Therefore, omega is exact. So if you have an action which is symplectic, you get for free that is Hamiltonian. And now, how did he end this proof? He ended this proof with a beautiful idea. If you are in a neighborhood of a point, to prove the root theorem, well, we all know it. To prove the root theorem, keeping track of some functions, it's quite easy. It's, well, it has a name, it's a theorem. It's a Rucca-Teodori theorem, which tells you that, okay, if I have n functions, I can have less than n functions that commute, I can keep track of these functions, okay? And the nice idea that he had is, okay, take Darbuka Theodori at a certain point, and now you have a Hamiltonian action of a torus. This Hamiltonian action of the torus is going to move this neighborhood, and you're going to get the whole neighborhood of the torus. That's the idea. So that's a lovely idea. That's what I have loved here. So that's an idea in which you put integrable systems and group action. And this idea, you can export it to Poisson manifolds, of certain type. I'll try, if I have time, because I don't know, I have a lot of slides. If I have time, I may say something like this. So integrable systems, therefore, are very close to toric symplectic manifolds, because this theorem shows, indeed, in particular, that you have an action of a torus in a neighborhood of a symplectic manifold. Okay, when this action is global, then you have what is called a toric manifold. But toric manifolds, therefore, I could think as a particular case of integrable system. Any toric manifold gives me an integrable system. Okay, toric manifolds are very specific. They are completely well understood. Indeed, there is this nice theorem of Del San that tells me that there is a one-to-one correspondence between toric manifolds and the image by the moment map, which, by the way, it's always a polytope. That's beautiful. Okay, applications. Well, I'm going to go very quickly because I only have 15 minutes and I went very slow. An important application of the action angle coordinate is to geometric quantization. Okay, we saw the first day of the conference by Schmidt, a very beautiful talk talking about formal quantization. Okay, but here I want to talk about geometric quantization, which is a different approach to quantization. And this picture is the idea of what is the status of quantization in mathematics and physics. Essentially, this is a mathematician working hard. He is a bit bald, so probably he is a bit old, okay? And the cartoon says, at this point, we notice that this equation is beautifully simplified if we assume that the space-time has 92 dimensions. That's a mathematician. And, well, the physicist, okay, the physicist here, we assume that he's already in heaven. So for some reason, the physicists go always to heaven. Think about it. But he goes to heaven, he goes to St. Peter, and he says, I still don't understand quantum theory. He says the truth. Okay, so, well, this is indirect to YouTube. Now I hope I don't have haters, but it's okay. So the idea is we have classical system, observables, and a bracket, which is a Poisson bracket. So again, the bracket there. And we want to, the idea is that we have to transform this classical system into some quantum system in which the observables, which are just functions, now become operators of a Hilbert space. And the quantum system is the Hilbert space. Okay, we have to, it's an equation in the Hilbert space. And the bracket becomes a commutator. So it's a 3-step process, very simple. Okay, what I'm going to do here is to say that it's possible to apply action angle coordinates to do a step 1, to find what is the Hilbert structure. In the case in which I have, for instance, an integrable system. Okay, now you're going to believe this is a lot of expression, a lot of words for slides. This is too much, but I'm going to say it in 2 sentences. Geometric quantization in a nutshell. What do we need? We need a pre-quantum line bundle, which, of course, needs to satisfy some conditions. First, my symplectic manifold needs an integral class, and then I know that there exists a complex line bundle with a connection such that its curvature equals omega. Okay, and then essentially the initial idea of quantization was, let's solve this equation. Let's look at sections of this bundle. Let's look at flat sections. And this is going to be the space. But if we put all the directions, we don't get any sections left. So it's not a good idea. So we need to choose a specific direction. And the direction that is usually chosen is called a polarization. If I have an integrable system, polarization is a general concept. Usually we look at it in the complex setting. But here I'm going to be very primitive. I'm going to say that an integrable system, because it's a Lagrangian foliation, is an example of a polarization. So if I use an integrable system, in particular, I can get a quantization of the system. That's what I'm going to say. But quantization, not in the case in which I have 1, 2, 3. In the case in which I have 1, in which will still, if I die and I still go to heaven, which it's very unclear to me, maybe I can still say, I don't understand quantum theory, but I could solve step 1. Okay. So, well, for this, what is the connection to action angle coordinates? For this, let me talk about what is a Bord-Sommerfeld leaf. A Bord-Sommerfeld leaf is a leaf of this foliation such that the flat section is defined globally, because a flat section doesn't need to be defined globally. So here, a very simple example. I take again the cotangent bundle of S1, okay? And I take the trivial bundle. I take a very simple omega. So I take the bundle, the line bundle is trivial, and I get this connection one form. In this case, many people here, for instance, Nikita, who is an expert in this, knows that the connection, I can write it like this. And a flat, if I look at the flat sections equation, then the solutions are of this type. So I get solutions that are some function in t plus an exponential of t theta, okay? Of course, if t is not an integer, this is not well defined for all theta, you understand? I need t to be an integer. Otherwise, this section is not global. So very simple. The solution is the Bord-Sommerfeld leaves are just the ones satisfied are given by this equation when t is an integer. Okay, well, 2 pi k. So because of the Arnold-Liouville theorem or Liouville-Miner-Arnold theorem, this example is the canonical one, because if I have an integrable system, it's regular, in a neighborhood, it's going to be the cotangent bundle of a torus, and I'm going to have a product situation. Therefore, this product situation is a theorem by Gilman and Stenberg, which tells me, look, do you want to quantize a system? Yes. Then just count the Bord-Sommerfeld leaves. This works perfectly for toric manifolds. So you have a toric manifold, the image is going to be your Sampolitop, and you can look at these points just counting the integer points of the lattice. Okay, you count how many of them you have, and then you know that you have a complex manifold of this dimension. And then you go to heaven, to St. Peter, and you have done step 1 of the quantization process. Just for toric manifolds, okay, this is a nice application of the action angle coordinates. So action angle coordinates give me quantization of toric systems, also of other systems, but I'm going to stop it there. And I'm going to now present, and this is another love moment, I'm going to present, there is love here in this slide. I can always look at the action angle coordinates. I can always think of it in a even simplest possible terms. Just saying that in a neighborhood of a Liouville torus, okay, instead of saying, oh, I have a fibration by torus, omega looks like that, the only thing I have, my system looks the same as the cotangent lift of a torus. So if I have a torus, if I have any group on a manifold, you know that the cotangent lift gives me for free a Hamiltonian action. Now, instead of any group, take a torus, okay? Take Tn, okay? If you do the cotangent bundle of Tn with the standard Liouville 1 form, and you do this computation, you find that the moment map is just given by the piece. So another way, and a very simple way to present the Liouville-Miner-Arnold theorem is to say that an integrable system is the same as the cotangent leaf of a torus in a neighborhood of the torus. And this is a very beautiful way to rephrase the theorem. So this is another connection to groups. Okay, what about singularities? I'm going to skip this. There are very nice pictures. Pau, I'm sorry, because I wanted to explain something we are doing with Pau. There was another love moment here, but I need to skip this because I don't have time. Let's talk, because I only have 10 minutes. Now it's when I'm going to say, oh, we started a bit late. Okay, I still not going to do it. Because we have 10 minutes. Let's talk about real life. Let's talk about the solar system. Copernicus, we revolve around the sun like any other planet. Kepler, planets spin in elliptic coordinates, in elliptic orbits. Ooh, this sounds like the Liouville-Miner-Arnold theorem. Let's talk about the n-body problem. Difficult things. Now, we have n-bodies that move. You can think that they are planets with their mass. Therefore, you have a gravitational potential. And the movement is conditioned by the masses of all. It's a very complicated problem. It's so complicated that it's non-integrable in general. But for two bodies, it's integrable. Okay, for two bodies, it's integrable because I'm going very quickly through my slides, but you're going to get the slides later on, because you have the total linear momentum and the total angular momentum that tells you that it's integrable. And what about the three-body problem, right? Well, the three-body problem is non-integrable in general. But here I'm going to present a simplification. Okay. I'm very happy to know that Cedric is going to talk about this problem in the talk after, so you cannot miss his talk, because I'm going to go very, very quickly through this example. And I'm going just to say that in some conditions, it's even integral. So if one of the masses is assumed, so the restricted three-body problem, what is the condition? Well, out of the three masses, you assume that one is a spacecraft or a satellite. Okay, this satellite that Jagna this morning was telling, I want the satellite to be back. This is true. So this satellite doesn't have mass. Okay, so not only that, you assume that the movement takes place on the plane, which is equal to assume something that we had in the two-body problem, that the problem was planar because the total angular momentum was preserved. So this is a simplified model. Even with these conditions, it's not integrable. But if one of the masses goes to zero, becomes integrable. Okay, I want to show you something peculiar about these equations. Well, these equations, these equations are, of course, they are Hamiltonian, and the Hamiltonian is, again, kinetical plus potential energy, where the potential is a gravitational potential, where the two masses here, one is mu and the other is 1 minus mu, because I'm normalizing, take a role. Okay. An important thing is that people who have been working in this, and initially McGehee, have always done the following change of coordinates. I divide by x, and I call this r. And then they say, okay, when x is equal to 0, I cannot make any sense of this. And now we are Poisson geometers. We are not symplectic geometers. We are more than that. We are Poisson geometers. So we look at this change and we look at the equation and we say, okay, this form is not smooth, but it defines a Poisson structure. Okay. So just to finish my talk, because I have 5 minutes, I'm going to give an action angle coordinate for this kind of situation. That's the only thing I'm going to do. So how do we call them? Which kind of manifolds I consider? Omega is of this form. Everyone here already by now knows that there is this log symplectic or bisymplectic manifolds that I can think as Poisson. Let me recall that I consider an even dimensional manifold with a Poisson structure such that pi n vanishes transversally. And, well, an interesting thing happens, which is, well, first of all, these manifolds are almost symplectic. They are symplectic everywhere except where pi n vanishes. And the nice thing is that on this codimension 1 manifold, you also have a Poisson structure. So if you want to prove something about integrable systems, well, you can look at these manifolds in 2 different ways. One way is to think that they are Poisson manifolds, and we have a Poisson action angle coordinate theorem with Camille and so on. But it's not good enough, because what is a Liouville torus? If I have a manifold of dimension 2n, I would like the Liouville torus to be of dimension n. So what we do is to increase the number of functions that are considered legal by including some functions that are not smooth. And we do this, indeed, we do this in 2 minutes. We do this using the language of B forms, which is a language introduced by Melrose. Okay, I'm going to go very quickly around this, but sometimes it's convenient to talk in the language of Poisson geometry, but now it's convenient to think that we can work with this Poisson structure indeed as forms. Okay, indeed, it's very convenient to talk of forms, because one of the things you can do is to prove a Darboux theorem, like the one I have here. These manifolds in dimension 2, they were introduced by Olga Rakho, who completely classified. Unfortunately, she passed away some months ago. And if you take any of her two-dimensional examples and you make a product with a symplectic manifold, you have an example of one of these log symplectic or bisymplectic manifolds. Okay, let's go back in business. Let's talk about, I'm going to skip this. Let's talk about this result because Jeff is here. Jeff is highlighted. I didn't know that Jeff was going to connect. So I'm going to talk about a result that I proved with Jeff and Anna Kissenhofer, and they are both highlighted here. And it's an extension of the action angle coordinate theorem to the setup, to this singular setup that is motivated by the restricted three-body problem. Okay. Indeed, I'm going to show the result. The result we proved is that we have an action angle coordinate that it looks very much like the action angle coordinate that we had in general, with the difference that I have a P1 dividing, but this is what I expect from these symplectic manifolds. But also that I have a constant multiplying, and this constant has a Poisson meaning, which is the modular weight. So it's related to the modular class of the Poisson manifold. So it's a Poisson invariant, and it's an invariant which is associated to the connected component of the critical set where your torus lies. I didn't explain, but look, I am in dimension 2 and I get a torus of dimension n. This means that I'm not considering only standard Hamiltonians. I'm including also log functions as good functions. And in order to do this, I need to formalize this in the language of V-forms. I'm not going to do this because this is a colloquium talk, so I will not enter in detail. But what is also funny, and this is another love moment, is that I can also present, we could also present this result as a cotangent model. And here the cotangent model is twist because the singularity is in the fiber, it's not in the bicotangent bundle. Okay, so that's another love moment of the talk in which we can describe any integrable system on this kind of manifolds where you have things exploding in a controlled way that you have in the restricted three-body problem. You also get this on a manifold with boundary. You also get this connected to the problem that Jagna was explaining this morning. I will not extend myself. And so that's nice to know that you can look at this as just as a cotangent model. So in a way, integrable systems and symplectic manifolds, or in manifolds that are almost close to symplectic, are always a cotangent leaf. So this is like Weinstein, any manifold is a Lagrangian. So manifold here, any integrable system is a cotangent, is like a cotangent leaf in a neighborhood of the torus, of course. The proof is the same. Of course, I'm not going to talk about the proof. I'm not going to talk about that we can prove Adelsam theorem. This is for another life. And I'm not going to talk about this. And I'm sorry because I wanted to here talk about results with Anastasia, but I knew I wouldn't have time. So this was like a last slide. But I want to get to my last slide. Who are the usual suspects? Well, look, yesterday it was 3 a.m. I have to confess my talk was not ready at 3 a.m. yesterday night. And then I thought, how should I finish my talk? And then I said, well, I'm going to thank everyone. I said, yes, thank everyone. Why don't I put a picture? And then I don't know. Well, I don't know. I had WhatsApp open. This is a picture that I looked on the 26th of November. Joachim, who is here connected, sent me this picture. Look, this is an impossible picture. Now it's impossible to be again sitting together. And the best we can do is this a picture that I took. I sneaked when you were all connected talking about things. I took a picture of the from YouTube. Okay, and this is the closest we can get today. But what I want to say is, well, I looked at this picture, and maybe because it was 3 a.m., I said, doesn't it look exactly like the usual suspects? Well, this is the kind of slides you do at 3 a.m. And look, indeed, it's like I told Anastasia, Cedric, who is here now. Well, Robert is not here. I could add you here. Joachim and Pau, they are sitting here. It's like I told them, you have to sit like the usual suspects, which is a wonderful film, by the way. I know you are very young, but it's a very nice. I like this film when I watch it. Probably now I wouldn't like it anymore. But then I looked at this and it looks like the usual suspects. So what I want to go back to the beginning of my talk, and what I want to say that the usual suspects, and I'm going to do this very quickly so people don't get tired. What I want to say, that is the slide I want to show, is that the usual suspects are no longer Liouville, Poisson, Minerly. The usual suspects is Cardona, Planas, Malbeva, Jeff Scott, Anna Kitzenhofer, Paul Mir. You are the usual suspects, and I want to encourage you to go on with this wonderful idea of the young Poisson. And I'm going to stop it here. I think I prepared too much material for 1 hour. I'm sorry. I hope it was understandable. I stop it here.
Thank you so much, Eva. Let's all give a wonderful round of applause to Eva for this terrific, absolutely terrific colloquium talk. Thank you.
Thank you, Eva, and thank you for indeed encouraging us to make this event, to make it happen for like all the time of preparation.
Absolutely.
It's a lot of work. I mean, it's like really you are doing a great job.
Absolutely.
Like
I mean, if I could say, if I could say, the origins of this workshop really began. In July, I think I gave a seminar talk in Barcelona. That's when Eva suggested that we should do something for young people, some kind of event for young people. And I think Nastya and I immediately kind of caught to that idea and started developing. And the result was this amazing event, which I'm very happy to be organizing. Very happy that it's going so well, but also very sad because it's about to end.
It's about to end, but you will do some other one soon. And yeah, this is amazing. Well, indeed, you visited Barcelona, of course, online. Everything was online.
Right.
Yeah.
Yes.
Everything was online. So thanks a lot for this invitation. I hope this was understandable. I'm ready to answer any question if you want to send me emails, because I imagine now you need to start. Cedric is the next one. Cedric, I'm sorry.
We could have a very quick. If there's a very quick question, that could be fine.
So you can leave questions on Slack or anywhere else. We'll transfer.
Yes, Eva, you're on Slack, I think, as well, right?
I'm on Slack. Yeah.
Yeah, perfect.
I pretend to be modern, so I install Slack and these kind of things.
Excellent. Okay, then let's relegate all questions to Slack.
Yeah.
Or email.
Or send me emails or whatever. And the slides will be available online, so you have more time. I'm very sorry because I really want to. I realize I prepared too much material, but feel free to ask me questions about things that were not clear or things that I couldn't mention on the slides. I will be happy to do this, to reply, to answer any question.
Okay. Let's give another round of applause.
To the next.
Let's give another. Yeah, this is like a question discussion. So let's give another round of applause to Eva. Thank you very much. Thank you very much for basically initiating this event. I really.
It's you. I would have totally impossible to do this like this. And I tell you, I mean, I think like. It's wonderful. I mean, you could only do this. I mean, only you and Anastasia and Beatriz and anyone else who wants to join. Like, it's wonderful. It's very refreshing. Thank you very much.
Thank you.
Thank you, Eva. And
okay, so let's
and we'll switch to the talk of Cedric without any break. Cedric, give us a sign.
Cedric, I'm going to make you a co-host now, and I'm also going to ask you to unmute yourself. I think I have unmuted yourself.
Hi, I'm here.
Yeah, hi.
Hi, Cedric.
Let me start the video as well. Hi, everybody.
Hi.
Hi, Cedric. Sorry, I robbed 5 minutes of your time.
No, that's perfect. That's perfect. I knew this would happen.
You can blame me. You can blame me.
I knew this would happen, Eva. So I'll share the screen and you tell me if you see.
We do.
Yep.
Okay.
Yeah, we see it really well.
Okay.
Okay.
Computer just told me that my internet connection is unstable. So if there are some problems, let me know. I don't know.
Yeah,
Okay,
worst case scenario, you could if it gets really terrible, you could switch off. That would help. But for now, let's keep it as is for now.
For now, it looks good. Yeah.
Yeah.
Okay.
So we are starting the last plenary session of this conference with a talk of Cedric Holmes, who'll talk about the singular Weinstein conjecture.
Okay. Thanks a lot, Anastasia. Thanks a lot, Nikita and Anastasia, for organizing this event. I think it was, well, I mean, it's still not over, but I think it was extremely well organized, and one could really see that you put like a lot of thought into this. So thank you very much. The subject of my talk is the singular Weinstein conjecture, and before starting, I would like to say that this is joint with Eva that you just heard speaking, so everybody here knows Eva. And the last part of the talk will be joint work with Eva and Daniel Baltasar from ICEMAT in Madrid. Like I will state like, no, I think I won't even state the joint result that we have with Daniel. So this is what you'll see in the parallel session. So everybody that wants to join, I'll talk about this in the parallel session. Okay.
Cedric, I think it unfortunately it would help to turn off the camera because you're breaking up a bit. Yeah.
Okay.
And also maybe collapse all of us so that your computer isn't streaming us.
Okay. Perfect. Okay. So I hope now it's going to be better. And so the subject of my talk is the singular Weinstein conjecture. And so let me just briefly say where this fits into the conference. So what we'll study is like the dynamics on a certain kind of Poisson manifolds that Eva was briefly talking about. So like I'll review all what Eva didn't, well, not all what Eva couldn't talk about, but some of the bits that Eva wasn't able to talk about. I'll go over this again here. So this is a great opportunity. And I'd also like to relate this to other talks that have been done here in this workshop. So in particular, what we'll do is like study Weinstein conjecture in a non-compact setup. And this is a little bit what we saw in like the earlier session. So for me, this was the morning session with Jangna that talked about similar topics, but we'll have a different point of view in this talk. So this is what this is how you should situate this talk. Okay, now I cannot continue. Okay. So this is the outline. This is fairly a lot. So I decided to prepare one slides for both the plenary and the parallel session. So we'll stop here. So for everybody that wants to join in the parallel session, I'll go over the 4 points here. So let me. Okay, this is very strange. Okay, sorry, I did something wrong. Okay. So let me talk about celestial mechanics to introduce you to the topic. So I know that this is really off topic for this audience here. So let me give you a very basic example. Well, very basic example, which is not so basic because it has been studied during many decades, which is the restricted planar circular three-body problem. So this is a particular case of the three-body problem where you have three bodies moving into space, which is the primary, the secondary, and the spacecraft that are being attracted following Newton's law. And typically what one would like to say is to study periodic orbits of the spacecraft. And so this is the three-body problem, and we'll do some simplifications here. The first simplification that we'll do is to assume that the spacecraft has in fact negligible mass. So, and this implies that the primary and secondary move following Kepler's law. And moreover, the spacecraft is assumed to move in the same plane as the primary and the secondary. So this is what restricted planar means. Okay, and then circular means that we further assume that the primary and secondary are moving in circles, okay, around their center of gravity. So, and we'd like to study periodic orbits of that spacecraft. So let me write down the potential and the energy. So the potential is a time-dependent potential because it's given by 1 minus nu over q minus qe plus mu over q minus qm, where qe is the position of the Earth and qm is the position of the Moon. And well, those are obviously time-dependent, the positions of the Earth and the Moon. And so the Hamiltonian is given by kinetic plus potential energy. And this is not a good Hamiltonian to study the energy on the periodic orbits on the level sets, because it's not a reserved quantity, it's time dependent. So because we're here in the circular setup, what we can do, we can pass to rotating coordinates, and this is a magnificent thing, because now this Hamiltonian is not time dependent anymore, it's time independent. So it's a preserved quantity. Okay, so the price to pay somehow is that it ceases to be potential plus kinetic energy, but you have some magnetic terms here, which can be interpreted as the centrifugal force. Okay, and it's classically very well known that this Hamiltonian has 5 critical points, which are the Lagrange points that we order with increasing energy. And what I told you is that we're interested in the periodic orbits of that Hamiltonian vector field XH. Okay, so I would like to, well, there are basically 2 big branches of mathematics, let's say, that study this. Eba mentioned one, which is the perturbative methods, namely KEM theory. So looking at this as like an integrable system and perturbing it. So this is one side of the story. Another side of the story is that is a little bit more recently, is trying to deal with this problem using contact topology. And this is a little bit what I'm going to explain. So let me briefly review what I mean by this. So if you have a symplectic manifold and you have a hypersurface in that symplectic manifold, what you can look at is Liouville vector fields that are transversed to that hypersurface. So if there's a Liouville vector field that's transversed to a given hypersurface, okay, this implies that the induced structure on the hypersurface is in fact contact. Okay, so you get a contact manifold with a contact form. And the nice thing is that the Reb vector field, so this is a vector field I'll define in a second for everybody to follow, is in fact a reparameterization of the Hamiltonian vector field on that level set. Okay, so studying the Reb dynamics is basically in that setup giving the Hamiltonian vector field. So there's a famous conjecture concerning those Reb vector fields, which is the Weinstein conjecture, which says that a compact contact manifold always admits periodic Reb orbits. So this is Weinstein conjecture. So let me tell you what this Reb vector field is, just for sake of clarity for everybody to follow. So this Reb vector field is uniquely defined by those 2 equations. So this follows from, in fact, from the contact condition that this defines a unique vector field. And this conjecture is in fact more than only a conjecture, because it is known to be true in many, many cases. So for instance, Pitabo proved it in 1986 for hypersurface of contact type in the standard symplectic Euclidean space. Hofer proved it in 1991 for over-twisted contact manifolds in dimension 3. So this is something that we'll talk about a little bit more in the parallel session. And in dimension 3, in fact, it's completely known to be true since 2007. And so this is, of course, for the compact setup. So for the non-compact setup, I refer to Jagner's talk and we'll talk about this as well, about the non-contact compact setup, but with a completely different point of view than. So let me just briefly talk about one paper. So that uses contact geometry to study the periodic orbits of the restricted planar circular three-body problem. So if you take now an energy that is below the first critical value of this Hamiltonian, okay, one can see that the level sets of this energy has in fact three connected components. One where the position remains close to the Earth, one where the position remains close to the Moon, and one where the satellite escapes to infinity, in fact. And so what Albers, Frauenfelder, Kurt, and Patanen proved, so I think this is 2012, is that that there exists, in fact, Liouville vectors, because by what we saw is that this hypersurface is contact, with the contact form induced by the contraction of the symplectic form with the Liouville vector field. So this is very good. But now if you want to say something about periodic orbits of the Rep vector field associated to this contact form, this is bad, because in fact this is not compact, and this is not compact because of collision here. So even though this space here is bounded in space in spatial coordinates, in position coordinates, in the momenta it's not bounded due to collision. Okay, so this is bad if you want to say something about periodic orbits. So the way to get around this is to consider a regularization of the two-body collision, and this space can be compactified. And this compactification, what they prove in their paper is that this compactification admits, in fact, contact form, has an induced contact form. And so now by Weinstein conjecture, this Weinstein conjecture applies in that setup, and you can see that there is a closed orbit in that setup. Okay, so but this is of course only for the regularized problem. So, and this is why we're not very satisfied about this, because like they cannot say, they changed the problem somehow. You cannot say where those periodic orbits are that they find. Okay, so our point of view is that like maybe they're on the collision set, and what one would like to say is like one would like to include those singularities somehow in the geometric structures to keep track of where those periodic orbits are, in fact. Okay, and the response to this is in fact the via BM symplectic and BM contact geometry. So this is a little bit what we're going to do. So what is this BM symplectic geometry? So let me briefly talk about this. So the manifold and infinity one can study the orbits not only. So the authors that we just saw study the restricted three-body problem, and what one can do is what people in celestial mechanics do a lot is that they study the manifold and infinity using McGehee change of coordinates. Okay, and this is being done to study the dynamics at infinity, in fact. Okay, so first what you can do, you can go to polar coordinates, which is this change of coordinates here, and then you go to McGehee change of coordinates. And this is, so this change of coordinates here is a symplectic change of coordinates, but this one here is not a symplectic change of coordinates. So what the symplectic form looks like is not a usual symplectic form anymore, but is a singular symplectic form. So it looks like this. Okay, and this is a B3 symplectic form that Eva was talking about. So here you see that there's a singularity in here. Okay, so as a symplectic structure, this is something that is not well defined, but if you look at the dual of this, you in fact get a Poisson, a well-defined Poisson bracket. And what we're interested here is the dynamics of the Hamiltonian vector field on this, not symplectic, but B3 symplectic manifolds. Okay. And so, as I said, this symplectic form is not smooth. Okay. But the dual of this is a well-defined object. And it's, as we all know, it's a Poisson vector field. Okay, so this is a very particular class of Poisson structure, and what we're interested in is the dynamics on this Poisson manifold. So this is the dynamics of a B3 symplectic manifold. Okay, so this is a brief outline of the talk that we're going to do. Or like this is the aim, let's say, of the talk. So this is we'll see this at the very end at the parallel session, is that in fact one can see easily that this vector field here that is radial in the momenta is a Liouville vector field that is transverse to the level set of this Hamiltonian for positive energy. Okay. And so if you do the same symplectic, the same change of coordinates, you get this B3 symplectic form. Okay. And so what one is interested in is the dynamics of XH. So, and as I motivated during the last slides, is that that the contraction of this symplectic form with this this Liouville vector field gives a contact form. But this is not entirely true here anymore because we have this B3 symplectic form. So first of all, what we need to study is like, what is this one form here? Okay, what is this? And what can we say about periodic orbits of the Hamiltonian vector field on that level set? Okay, using this geometric structure here, which will not be a smooth geometric structure. It won't be a smooth contact form, but something more general. Okay. So, and this is what we'll study in the symplectic and the contact geometry. Okay. So let me give you the slides that Eva can give to you. So first of all, what is a B-symplectic structure? So a B-symplectic structure can be seen as a symplectic structure model of a Lie algebroid, which is in fact the B cotangent bundle. Okay. So this B cotangent bundle, how can you construct it? Well, a way to construct it is to look at a vector field that are tangent to a given hypersurface. Okay. And then the B tangent bundle is given by the bundle whose sections are in fact give you back those vector field that are tangent to the given hypersurface. Okay. So well, here I repeat this. So let us assume that we have a fixed hypersurface with a given function on this hypersurface, and you'd like to look at vector fields that are tangent to that hypersurface. Those vector fields are locally spanned by those vector fields here. Okay, and then there's the theorem of Swan that tells you that there exists, in fact, a vector bundle whose sections are given those vector fields that are tangent to that given hypersurface. Okay, and so now we have that vector bundle, and we can dualize this, and we can take sections of the wedges of this dual bundle to get forms. And so to talk about symplectic geometry on this, we extend the exterior derivative, and this is being done in the following way. So the given K form can be always decomposed as follows. So a K form of a B form of degree K can always be decomposed as omega equals alpha wedge df over f plus beta, where alpha is a smooth form of degree K minus 1 and beta is the form of degree K. And so the exterior derivative can be extended as follows. So you apply the differential to omega using this decomposition. You just apply to d alpha wedge df over f plus d beta. Okay, and this is clear that this d squares to 0 and is an extension of the usual round derivative. So now we have everything to define the main objects of this talk, which are B-symplectic forms and B-contact forms. So B form of degree 2 is said to be B symplectic if it's closed for this differential that we just defined, and it's non-degenerate as a 2 form for the B tangent bundle. Okay, and similarly we define B contact forms as B forms of degree 1 that satisfy this non-integrability condition here. So let me now just briefly situate where those things live in. So we have the symplectic world here, we have the contact form here. So this B symplectic forms are a generalization of symplectic forms, and B contact forms are a generalization of contact forms. And as Eva told us, is that like those B symplectic form are a very particular case of Poisson manifolds. So this is included in here. And now the very global picture will be the one of Jacobi manifold, which is in fact, so B contact forms can be seen as a particular case of Jacobi structure. Okay, so this is what I'll talk about a little bit in my parallel talk. So let me now finish with announcing the result that I'm going to talk about in the parallel session. So what one can prove is that if you have a BM symplectic manifold and a Liouville vector field, so this is a Liouville vector field, and this is a vector field that satisfies this identity here, that is transverse to a given hypersurface, then this hypersurface is in fact B contact. And so this is exactly what we need in the restricted three-body problem. So this would answer the first question of the two questions that we had in the restricted three-body problem. And so now if we want to say something about the periodic orbits of that red vector field, we need to analyze the dynamics of those B3 contact forms. Okay, so here are the results that I proved together with Eva Miranda. So first example is that in fact there exist compact examples of B contact manifolds without any periodic orbits away from the critical set. So this means that there's in fact no hope to really have like a Poisson conjecture for those B contact manifolds. Okay, but good news is that in dimension 3 and for a critical set that is in fact compact, there exists always infinitely many periodic Weber orbits. So even though there can be there can be examples without periodic orbits away from Z on Z in dimension 3 and Z compact, there are always infinitely many periodic orbits. Okay, and if you want to assure that there are periodic orbits away from the critical set, you can in fact impose some necessary condition, which are the conditions of being over-twisted away from the critical set and some R invariance around the critical set to show that there exist in fact periodic orbits away from the critical set. So I won't go into the technicalities of those two definitions here, but in the parallel session I'll give some more motivation on those. Okay, this theorem is interesting because it is in fact it gives you a necessary condition on non-compact manifolds to have periodic orbits away from the critical set. And last but not least, so this is what I declare to be the aim of this talk, is to go back to the restricted three-body problem. So what we can prove in the restricted three-body problem is that after McGehee change of coordinates, in fact, this manifold here is a B3 contact manifold, okay? And in fact, it's non-compact, so a priori, there's no hope for it to have periodic orbits. But what we prove is that on the critical set, there is in fact infinitely many periodic orbits, even though the critical set is non-compact. And hence, like the last result that I mentioned here doesn't really apply, but one can compute this directly. And so this is what we can prove. Okay, so on the critical set, on the restricted three-body problem, we have infinitely many periodic orbits. And so what I'll talk about in the parallel session is how to generalize the Weinstein conjecture, because Weinstein conjecture, as we saw, is not true as such, because there can be examples without any periodic orbits away from the critical set. But what we conjecture is that, in fact, you always have this behavior here. You always have what we call singular periodic orbits, which are orbits coming from the critical set and going to the critical set. So this is what we call a singular periodic orbit. And what we conjecture is that this is in fact always true. And I'll talk about some recent progress that we did in this conjecture here. So this is everything that I'll talk about here. So thank you very much for your attention, and I hopefully see some of you in the parallel session.
Thank you very much, Cedric. It was a wonderful talk. Let's everybody give Cedric a round of applause, including emojis. Let's everyone use our emojis.
Thanks.
Thank you. Okay, and then so without further ado, let's move on to our next speaker.
Tobias.
So where is Tobias?
Right here.
Hi, Tobias. I will make you a co-host, and I will also ask you to unmute yourself.
Okay, thanks.
Okay. Great.
Cedric, can you stop sharing your screen?
Yeah, I'm trying to do this, but I kind of lost on my own computer.
Okay.
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 I've done it for you.
So I can share now?
Yes, you should be able to share now.
Okay.
Okay.
And whenever you're ready.
Okay, I'm ready. Yes.
Okay. So we continue our session with Tobias Diez, who will talk about group valued moment maps for diffeomorphism groups.
Yes, thank you for the introduction. And first of all, thank you to the organizers for organizing such a wonderful conference. All the hard work that you put in is really showing off, and it's really interesting. So thanks a lot for this. Yeah, so I will talk about group valued momentum maps, and this will be a joint work with Tudor Ratio. Yep. And everything started about 5 years ago with a really basic observation that there are certain moduli spaces, and these moduli spaces often carry a symplectic structure. And so when I say moduli space, I mean that we have some geometric object and we put some conditions on it, and then usually there's also an equivalence relation, so that they quotient out. So just like look at some simple examples. For example, the projective space. So we take all the lines, which is parameterizing all the lines. So you can rewrite this as looking at all the vectors which have norm 1, and then you quotient out by the reparameterization action, which is U1. And there's the well-known Fubini study metric there, which is a Kähler structure. So in particular, you have a symplectic structure. So that's a really easy, simple example of a moduli space, which is symplectic. I'm a bit more interested in the infinite dimensional moduli spaces, or things that are coming from infinite dimensions. And one of the classic examples is the Atiyah-Bott construction. So Atiyah-Bott looked at a principal G bundle over a Riemannian surface, and then they looked at all these connections which are flat, and modeled out by the symplectic, by the action of the gauge transformations. And it turns out that these moduli spaces is also symplectic. And another really well-known example is the so-called Teichmüller space. There you also start with a surface, and you look at all the Riemannian metrics that have a constant scalar -1. And then this time you don't quotient out by some gauge transformation, but by the reparameterization action given by the diffeomorphism group. And it turns out again that the Teichmüller space is a symplectic structure, which in this case was proven by Wild and Peterson. So you already see a simple example where symplectic geometry comes in again. For example, that you see that even numbers are popping up everywhere. So you see that you need 2 persons apparently to endow moduli spaces with symplectic structure. So that's a particular case there where even numbers come up. But there's another example where symplectic geometry comes up. Namely, we want to realize these spaces as symplectic quotients. So as moduli spaces in the symplectic category. So that's really easy in the first tool. examples. So the projective space is classic, that this is one is a symplectic quotient. And RTR bot showed the same, that a modular space of flat connections is a symplectic quotient. Okay, what about the Teichmüller space? Is this also a symplectic quotient or not? And that's what I want to be answering in this talk today. Yeah, and one of the most ingredient or important questions there is, of course, that we need a momentum map for diffeomorphism groups, so that we can realize the scalar curvature as a momentum map. And that will be one of the main tasks in the talk. So let me review by some classical things that everybody should know. So we start with a symplectic manifold in a closed non-degenerate two form, so nothing fancy, no singularities, nothing. And we have a Lie group acting on M, which preserves the symplectic structure. And then we can require that there exists a momentum map, which is a map from the symplectic form, symplectic manifold to the dual of the Lie algebra, and which satisfies this relation that killing form, the killing vector fields, or the fundamental vector fields generated by the Lie algebra action are given by the exterior derivative of the momentum map. And it's the standard Marsden-Weinstein symplectic reduction theorem that if you take the level set of the momentum map and then quotient out by the Lie group action, that you can get again a symplectic manifold. Of course, for this you need some requirements that you really get a manifold and not a singular space, but let's ignore these things for now. And the question is now, do we have such a thing, a symplectic structure and action of the diffeomorphism group and a momentum map so that we can realize the Teichmüller space as a symplectic quotient? And before I come to this, let's start with a simple example where we have an action of the diffeomorphism group and can ask, okay, does there exist a momentum map for this action? So we start with a compact manifold, which has a volume form. And so this is S. And then we have a symplectic manifold as a second ingredient. And we look at all the functions from this compact manifold with volume to the symplectic manifold and all the smooth functions. And we put a symplectic structure there. And so if I put a symplectic structure there, we need three things essentially. So the input is that I have a function, that's the point, the base point. And then I have two vector fields which are tangent to this function that I picked. So this will be vector fields along this function. And what I do is that I plug in these two vector fields that I got into the symplectic form, and then I get a function on S, and I integrate this function. And it turns out that this one is really a closed two form on the space of two smooth functions from S to M, and it's non-degenerate. So it's really a proper symplectic structure on this infinite dimensional space of smooth functions. And there exists a natural diffeomorphism action just by reparameterization of the smooth function. And it turns out that this action is symplectic if we restrict to a diffeomorphism that preserves the volume that it's fixed on S. Okay, so we have all the ingredients that we need for symplectic reduction, except that we need also to say what a momentum map is. And for this, we need to say what the dual of the Lie algebra. So have a look at this. So volume preserving vector fields can be identified with a closed n-1 forms. And then if you take the dual, you get one forms on S modulo the exact ones. And the pairing is just by integration. And in this way, the dual is given by the small forms modulo exact ones. And then it's a relatively straightforward calculation that the momentum map is given by the pullback of the preform of the symplectic form. So we have to assume that the symplectic form is exact, and then the momentum map is given by the pullback of this preform of the symplectic form. So that sounds really good, but there's also an important observation, namely that this momentum map doesn't exist anymore if the symplectic form is not exact. So this was observed by François Guémama and Cornelia Wiesmann. And so that's a really important problem that we have to deal with the case when the symplectic form is not exact, and then there doesn't exist a symplectic momentum map anymore. And the reason is that there exist topological obstructions. In fact, it's exactly the pullback of the symplectic form in the cohomology class of this one. That is the obstruction for the existing of a classical momentum map. So there's some topological data that obstructs the momentum map, and we were wondering about this problem for some time until we realized, okay, it's not a problem, but it's actually a feature of the whole theory, namely that the diffeomorphism action sees some topology. And then you would also expect that some conserved quantities are topologically. But so usually their topological information is discrete, but there's no space to encode discrete topological conserved quantities in a momentum map, in a classical momentum map, because this one just takes values in a vector space, essentially. So there's no discreteness anywhere that we can use to kind of like store these discrete topological information that is conserved under diffeomorphism actions. So this leads us to kind of like generalize the notion of a momentum map. And we take some inspiration by Poisson geometry. So let's review a bit of classical notions from Poisson Lie group actions. So we start with a Poisson Lie group that is kind of like just a Lie group and carries a Poisson structure such as the multiplication and inverse Poisson maps. And then you see that the Poisson structure vanishes at the identity element, and we can look at linearization. And it turns out that this one defines a Poisson Lie algebra structure on the dual of the Lie algebra that we started with. So we can integrate this dual Lie algebra structure and get a simply connected Lie group G star. And suppose now that we have an action of G on some Poisson manifold in such a way that the action map is a Poisson. And then we can ask that the so-called Blue-Weinstein momentum map, which satisfies a similar relation, which relates the Poisson tensor to the linearization of the action. And if the symplectic manifold, if the manifold that we started with, this Poisson manifold, actually turns out to be symplectic, then we have a similar formula than as before for the classical momentum map, except that now the exterior derivative is replaced by this so-called logarithmic derivative. So J is really taking values in the dual of the Lie group, so in the dual Lie group, and we have to take the logarithmic derivative, which is a Lie algebra valued one form on M. So this is the basic starting point in observation, that these Lie group valued momentum maps can be actually generalized. So we started with this Poisson Lie group, but actually the concept that we came up with, these Blue-Weinstein momentum maps, doesn't need anything about the Poisson Lie group structure on G anymore. So it completely makes sense if you just look at some arbitrary dual Lie group, which has some Lie algebra of the dual of the original Lie action, but we don't need any Poisson structure anymore there to define this. So let me formalize this a bit. So we look at the following setting now. We have a symplectic manifold, and we have a Lie group G acting on M. And we assume that we have some given Lie group G star, which has a Lie algebra as a vector space, the dual of the original Lie group G. And then we say that this action admits a group valued momentum map, which is a map from the symplectic form to this dual Lie group, such that this relation holds, where again this delta is now the logarithmic derivative. So that's what is the definition of a group valued momentum map. And you see that there we recover the usually momentum maps as special cases. For example, if we take G star to be just the dual of the Lie algebra, so just as an abelian Lie group, then we recover the usually momentum map. but G star doesn't need to be simply connected or connected. And this one is really handy because we can also recover circle valued momentum maps. Maybe a G star is U1, or also cylinder valued momentum maps, which are discrete quotients of G star. And there's an important example, the symplectic torus, which we have a closer look now. So we start with a symplectic vector space and some letters acting on this vector space, and a symplectic form on V, which is invariant under the lattice, and thus this can to the symplectic torus. And we have a natural action of G by translations. It is relatively easy to see that this action does not have an ordinary momentum map, which takes values in the dual of the vector space, just for cohomological reasons. But in fact, it turns out that there exists a group valued momentum map. So what is the dual group? And the dual group in this case is that we take the dual of the vector space and then quotient out by the dual letters. And the group valued momentum map has a simple formula. Namely, it's given by just plugging in the vector into the symplectic form to get a dual element. And this formula makes sense under some integrability condition, namely that as soon as I have 2 points in the lattice and I plug them into symplectic form, I need to get an integer. So if this integrability condition holds, then I get this formula defines it gives us a well-defined map, and this one turns out to satisfy the group value momentum map relation on the previous slide. So the takeaway message from this example is that there exist group value momentum maps even when there are no ordinary momentum maps, but it's not always the case that there exists a group value momentum map. I mean, for example, if the symplectic form here is not satisfying this pre-quantization principle. Okay, if I say momentum map, then I need to justify why I say momentum map, and it's not because it generalizes over momentum map, but because it really there's a general form of a Noether theorem. So the input is as in a classical Noether theorem. So we have a symplectic manifold, a Lie group acting there, and we assume we have a group valued momentum map now instead of the classical one. And we have an ordinary Hamiltonian, which is G invariant. And then it's as in the classical proof, you show that then the momentum map is actually constant along the integral curves of the Hamiltonian flow. And the important difference to the classical Noether theorem is that we are now getting conserved quantities which have some topological character. For example, the easiest one is that I just compose the momentum map with the map that projects to the connected component of the group. And then this Noether theorem tells me that this map is a constant along the integral curves of the Hamiltonian flow. So I get discrete topological information encoded in this non-trivial topological structure of the dual group. Okay, so now let's come back to this example that we looked at the beginning, that we looked at smooth functions from a volume manifold to a symplectic manifold, and see if we can improve this one to also have a more general momentum map in this group valued momentum map setting. And so we need a Lie group that integrates this dual, which was this one forms modular the exact forms. And the best way to motivate the Lie group that we choose is by reinterpreting what one form means. So we view in this case the one form as a connection one form on a trivial circle bundle. So that's just a reinterpretation. There's a one-to-one connection between connection one forms on the trivial bundle and ordinary one forms. And gauge transformations are exactly just smooth functions on S, where actually U1 valued functions, but in this case it doesn't matter. So, and these act by gauge transformation, and gauge transformations is exactly that you take the exterior derivative. So in this case, we get a reinterpretation of this dual space of one forms modulo exact forms as the space of connections on the trivial bundle modulo the gauge transformations. And now that there's a really straightforward generalization, what we should maybe pick as this dual Lie group, namely we just remove that at all isomorphism classes of U1 bundles with some connection, modulo gauge transformation, without requiring that a bundle needs to be trivial. If you know a bit of differential characters, then this is the so-called second Checker-Simons differential group. And there are two important observations. Namely, first, that this group is not connected because there's a natural map to the integral valued second homology class. And it's also not simply connected because it contains the dual torus. So the important observation is now that we get a group valued momentum map, which takes values in this group of isomorphism classes of principal bundles with connection. So previously we had to assume that this symplectic form on M was exact, and we can now relax this condition by just assuming that it has a pre-quantum bundle L with some connection theta. And then it turns out that the momentum map, the group valued momentum map, is given by the pullback of this pre-quantum bundle to S. And these two phenomena that I described before, that the group is not connected and not simply connected, has some applications for Clebsch variables and also for recovering some other topological information, for example, the Liouville class of a Lagrangian embedding, in terms of these non-trivial topological data encoded in this group valued momentum. Okay, so that's already at the end of my first part of the presentation. So I introduced these group valued momentum maps, and they were inspired by the Lou-Weinstein momentum map in Poisson geometry. And we saw that these group valued momentum maps exist more often than ordinary momentum maps. And they have this important property that they encode discrete topological conserved quantities. And we saw that diffeomorphism groups have momentum maps under some condition of existence of some pre-quantum bundle. And in this case, they take values in groups of circle bundles with connection. And in the parallel talk, in half an hour, 1 hour, I will explain a bit more in detail how this is now connected to the original question of can you actually realize the Teichmüller space as a symplectic reduction? And we also have a look at equivariance properties of group valued momentum maps, which will have some interesting connection to Poisson geometry. And with this, I thank you.
Thank you very much, Tobias. Let's everybody give a warm round of applause for Tobias for this wonderful talk. Let's use our emojis as well. Emoji applause. Thank you, Tobias. So we'll move on to the next speaker right away, but we should take a very short break. We were behind schedule, but now I think we are on schedule.
Yeah, we're right on time.
So, yeah, we're right on time.
Yeah, Mikael, you can start, well, after you made the co-host, you can start sharing your
so
slides.
I've made you a co-host.
Okay, yeah.
So you should be able to share your slides now.
Okay, we see them.
Yeah.
And now we see them perfectly.
Yeah.
Okay.
Perfect.
And we still have 4 minutes. Yeah,
so we taking these few minutes to stretch a bit. Everyone sitting in front of their computers, stretching is always a good idea, even if you're live on YouTube.
But yeah, I'm serious that we should prepare ourselves for the next workshop and get some basic routine that we put in between the talks.
I think so. Yeah, I think so. Joel, I like what you're doing. Yeah, I'll do the same.
What's Joel doing? Oh.
Yeah, I mean, people do this, like they earn money with this. They just stretch and do all kinds of exercises in front of the camera on YouTube, and they get paid. you know, we should get in on that too. Perhaps hire a yoga instructor to give a Zoom lesson. I think that's a great idea. Yeah.
Right.
Like, as a conference, we're not asking for much funding. This could be, this is totally something we could ask for.
Next step would be reimbursing for food.
Right. Yeah, Javier is actually absolutely right. Yeah, there are people who literally just eat in front of the camera and get paid. I mean, there's all kinds of hilarious on YouTube that people get paid for just because they have like thousands and thousands of viewers.
Can we not proceed with this discussion?
Yeah. It's a bit depressing. It just makes you kind of suspect maybe you're in the wrong business.
How many views do you need to get monetization on YouTube?
You need, I think you need 1,000 subscribers to be able to start monetizing from your channel. Yeah.
Okay.
I have, I think, around 120.
128. This is coincidence? Don't think so.
Right now we are 60, so it's not so bad.
There are also 5 people watching on YouTube.
Everyone should subscribe to Nikita. I agree. I didn't want to say it explicitly.
Yeah. But I strongly recommend doing it. You'll get notifications and live streams. And we are about to start.
Right. Yeah. I think you can begin whenever you're ready.
Okay, so our next speaker for today is Cueca, who will speak about the cohomology of current algebroids and the characteristic classes.
Okay, so first of all, I want to apologize myself for my intervention yesterday in a parallel session. So I just want to say that here. And second, I want to thank the organizer for the opportunity to speak here in this conference. So I think that it's really nice to see young people that give to us the opportunity to also speak. So third, I want to say that this is a joint work with Raj Mehta of Smith College, and it's already on archive, so you just can take a look there. So, okay, so let me go ahead and just try to say what is this talk about. So this talk is just about produce new invariants for current algebroids. And when I say invariants, I just will say kind of cohomological invariants. And by that, I mean that current algebroids have an associated differential complex, and then they have an associated cohomology. But this cohomology and this differential complex was not so easy to work with, to study, and then we will just build an explicit description of this differential complex, and that includes some Cartan calculus. The second thing, just we will explain what are representations of a current algebroid via just vector bundles with connections. And third, we will introduce these new invariants that are just characteristic classes on this cohomology associated to the current algebroid. So let me say that this is just an analogous picture of what happens for Lie algebroids. So suppose that you have a Lie algebroid, then it is well known that the sections of the exterior power of the dual vector bundle inherit a differential complex with a differential satisfying this kind of Cartan-like formula where you use just the anchor and the bracket of the Lie algebroid. And then it is also well known that representations of a Lie algebroid are in one-to-one correspondence with vector bundles with flat connections. For many propos, maybe you should extend this definition to representations up to homotopy, but I just want to say that the basic representations are given just by vector bundles with flat connections. And then Marius Kreinit and Rui Locha Fernandez were able to construct secondary characteristic classes coming from that joint representation that for Lie algebroids is something up to homotopy. So what we want to mimic in this talk is just this scheme for current algebroids. So let me say some words about current algebroids and maybe just start for a motivating example. So what is a current algebroid? So suppose that you have just your manifold and then take your tangent plus cotangent and sum it. Then on this vector bundle, you have the pairing between vectors and covectors, and you can project also to the tangent bundle, and then you can create this funny bracket. What is important of this bracket is that appears historically in many situations. For example, the first appearance was in constrained mechanical systems. So if you want to study mechanical system with constraints, that the previous talks shows you many of these situations, then the current Dorfman bracket appears naturally. Another thing is that many integrability conditions of geometric structures can be also codified as some involutivity for subbundles in this Tn plus T star n. For example, if you have a two form, the two form is closed if and only if the graph of the two form is involutive under this bracket. The same for a bivector. A bivector is Poisson if and only if the graph of the bivector is involutive with respect to this bracket. Or for example, generalized complex structure were also involved in these current algebra things. So let me give right now a definition. So what is a current algebroid in this talk is just a vector bundle endowed with three structures. First of all, a non-degenerate symmetric pairing, then a vector bundle map, call it the anchor, and then a bracket. Now, the structures, what satisfy is that basically the bracket is a derivation of himself, of the anchor, and of the non-degenerate symmetric pairing. And then we have this four item, that is that the bracket is not skew symmetric, but the skew symmetry is controlled by the pairing. And this is what makes the difference between current algebroids and Lie algebroids. First, we have a pairing, and this pairing is what is controlled, the skew symmetry, or better say, the non-skew symmetry, the loss of skew symmetry of your current algebroid, of your bracket. And then what happens is that the theory complains becomes completely different from the study of Lie algebroids. And now let me give some more examples. So for example, if your base manifold, if your vector bundle is just over a point, so if you have just a vector space, then this reduces to a quadratic Lie algebra, that is a Lie algebra, and though with a pairing that is ad invariant. So why right now is really a Lie algebra is because it's controlled by the pairing, but you have this big D that is coming from the base. So if this big D is just zero because you don't have anything on the base, then your bracket is skew symmetric. But it's the only situation where the bracket is skew symmetric. So another example is just the same as before, as I give as a motivation, but now twisted with a closed three form. So the H right now is a closed three form on your base manifold, and then you can contract with two vector fields and get just a one form. And this is also another example of current algebroid, or more generally, if you have a Lie bialgebroid, then on the sum of the Lie algebroid plus the dual, you can also construct a canonical current algebroid structure. So this are more or less the main examples. And what I want to say is some just motivations that can be useful. So for example, if you are aware of just topological field theories, so there is one that is given by a current algebroid, that is the current sigma model, and this includes the Chern-Simons theory, because quadratic Lie algebras are an example of current algebroid. Another motivation can be quasi-Hamiltonian, the study of quasi-Hamiltonian spaces or Poisson-Lie duality, in order to see these dualities or these quasi-Hamiltonian spaces. Really is useful to go to current algebroids, or to study Manning triples and Dirichlet doubles also is useful to go to current algebroid. Or if you have a vertex algebra, the truncation up to order 1 give you also a current algebroid. Or for example, a current algebroid give you a two-term L-infinity algebra. That means that appears naturally in higher homotopy structures over there. So there are many motivations of why you should be interested in studying current algebroids. And maybe if you are just a Poisson geometer, I just want to say that for many cases to make, I don't know, pullbacks of Poisson structures or to study reduction of Poisson structures, you naturally must go to the current algebroids world. So current algebroids is something that appears naturally in many places of mathematics. So let's now go to our point. So I promised you that current algebroids have a differential complex, but where it is? So the point is that we just need to change our point of view. And this is made by this theorem, this several Reutenberg correspondence that says that a current algebroid is in one-to-one correspondence with degree 2 symplectic Q manifold. I don't want to explain right now what is a degree 2 symplectic Q manifold. I will do it in the parallel session. But the important thing is that these graded manifolds, the functions on these graded manifolds have degrees. And now the fact that you have this Q structure is just the same as saying that the functions on the graded manifold inherit a differential. So this Q that is increasing the degree by 1 and the Q squares is equal to 0. What happens is that then you have a differential complex associated to a current algebroid, just this function with a Q structure, but this is not really hands-on. So it's just an implicit description. So can we make a better description of this complex, and can we find any Cartan-type formula for the differential, for example? And the answer is that we need to change a bit our point of view, and what I want now is just to describe, given a vector bundle with a non-degenerate pairing, I can construct K cochains of the following way: are elements that each K sections of your vector bundle and returns you a function, but now when you swap two elements, they are not skew symmetric, so they are not sections of the wedge as happens for Lie algebroids, but the skew symmetry is controlled by some symbol map. That is something that is K minus 2 sections and returns you a vector field. And this is the equation that defines your symbol map. So now, given a vector bundle with a non-degenerate pairing, I constructed this Keller-Waldman algebra that I will denote it by C bullet E. And what happens is that the pairing naturally extends to this whole algebra and gives you a degree minus 2 Poisson bracket over there. And in addition, if your vector bundle is a current algebroid, then you can create this degree 3 cochain. That is just the contraction of the bracket with the pairing, and the current actions are equivalent to the fact that the differential given by just first slot with this 3 cochain is really a differential. So this equation tells you that Diez squares is equal to 0. And this is why current algebroids have now a cohomology. But okay, I just introducing for nothing this thing. And I already tells you that current algebroids have a differential complex from this perspective of graded manifolds. So what happens? And what happens is that this is our first theorem, is that if you have a current algebroid, the two differential graded algebras that I introduced here are isomorphic naturally. And the isomorphism is really natural. And the second thing is that really this differential that we construct have a Cartan formula that is really analogous to the Cartan formula for Lie algebroids. But now you see, since these cochains here are not skew symmetric, if you want to put this bracket at the beginning, as many times is do it, then the symbol map starts to appear. So you need to be a bit carefully how to just go from one side to the other. And I want to say that this Keller-Wallman algebra was introduced like 10 years or maybe 15 years early by Keller and Stefan Wallman. And they just didn't prove it, these isomorphisms, because they were working in an algebraic setting for current algebroids. Okay, so now we can go to the second part, that is representations of current algebroids. And I want just to give a definition. So given a current algebroid E and a vector bundle, I define an E connection on that vector bundle by this rule here that is a section of the current algebroid and a section of the vector bundle, and return just a vector bundle section that is satisfying this Leibniz rule in the vector bundle argument and this linear in the current slot. So what happens is that during many times, this kind of E-connections was appearing in the literature, but the curvature of an E-connection was really difficult to make sense of. So, you know, the curvature, you can define it as usual, just the commutator of this operator minus the bracket of the two slots here. And now, with our point of view, it's really easy to see that the curvature become just an endomorphism valued to cochain. And maybe since the cochains are not skew symmetry, this was part of the difficulties of the definition of the curvature for connections. And now let's make the link of this. So something that I want also to say is that sometimes people also require some compatibility with the pairing, but this is not something necessary in our work. We believe that it's just auxiliary. So then I want to stress how this is related with representations. And then, so given an E connection, I can define an operator just on the space of cochain tensor the sections of your vector bundle, as is do it for Lie algebroids, everything is completely analogous. And what happens is that there is a one-to-one correspondence between E connections and these operators here on this complex. Moreover, the curvature of the connection is equal to 0, so the connection is flat if and only if this operator here squares to 0. Therefore, we can say that representations of current algebroids are in one-to-one correspondence with flat E connections on a vector bundle, as usual. So now, well, and also some Bianchi's identities holds in this setting. Okay, so now what happens is that if I have my current algebroid and I pick an auxiliary linear connection, so just a TM connection on E, I can build an E connection on E by this formula over here. And this formula really resembles what happens also for Lie algebroids, but without this term, this last term that is coming, let's say, from the cotangent bundle composed with the metric. And the important thing of these connections that are not canonical because depends on your choice of linear connection is that independent of the choice of your linear connection, they are always compatible with the pairing. and they are not flat because this linear connection is just destroying the adjoint property of the Courant bracket. But since they are compatible with the pairing, you can prove that the trace of the curvature is equal to 0 when k is odd. So you also can build connections on Tm and T star n given a linear connection, and you can put it together, and on Tm plus T star n, this is also respecting, is just well compared with the pairing as happened in the previous case. So once we have that, I can go to these characteristic classes that are the cohomological invariants of my current algebra, right? Okay, so the first one is the modular class. So how is the modular class defined? So I need a vector bundle with rank 1 with a flat connection. So just a rank 1 representation of my current algebra. And what happens is that this B defines for you a cohomology class in a degree 1 cohomology class. And this is called the modular class of the vector bundle B. And we denote it by this psi B. So for current algebroids, since we develop a whole Cartan calculus that I will explain in the parallel session, one can see that for wedge top of E, there is a canonical flat E connection given by just Lie derivative along E that of this top form. And this is just like the bracket applying as you expect. So this is just the contraction of E times dE plus, so by the Cartan, the usual Cartan formula. So there are many ways to define this, but it's completely canonical. And what happens is that the modular class associated with these rank 1 vector bundles is always 0. So this is really different for what happens for current, for Lie algebroids. Lie algebroids in general are not unimodular, but here the presence of the pairing makes current algebroids unimodular. And this is what not surprised, because quadratic Lie algebras are always unimodular. And then we are just extending what happens over a point. Okay, so I want to remark that this was already defined, this modular class, this intrinsic modular class was already defined by Stianon and Pinchot. They just didn't notice that it's always equal to 0. Okay, so if we don't have the modular class, what else we can do? Okay, maybe we have primary characteristic classes. So what are the primary characteristic classes? This is just giving an E connection on a vector bundle. I just can consider the trace of powers of the curvature. And this gives me a 2K cochain. So what happens is that, as in classical theory, first, this gives you really a cohomology class, so a characteristic class. And the second thing is that it's really independent of the connection you choose in order to define this. So if you have an E connection on a vector bundle, this class is just intrinsic and we'll denote it by this chair class of B. Okay, and then is a class on degree 2K of E. So what we see it here is that we have this adjoint connection. So we have given a linear connection on E, we define it an E connection on E, and we define it E connections on Tm, T star m, and Tm plus T star m. So our first proposition is that for a current algebroid, the primary classes of the E connection on E are equal to the primary classes, to the chair classes of the E connections on Tm plus T star m. And these are just topological. So what happens is that this doesn't have any kind of information about the current algebroid structure. So really don't give you new classes for current algebroids or intrinsic classes for current algebroid. So then we need to go further, and we need to go to the secondary classes, and we can define in that. So given just two connections on the same vector bundle, we can produce a Chern-Simons type transgression form that this is a cochain on 2k minus 1 of E. And what happens is that you can see that the differential of this cochain is equal to the primary classes of the two connections that we already have it. So if the primary classes vanish, then you can create these secondary characteristic classes. And then you have now a way to produce maybe interesting things. So let's go. Given a current algebroid, then I choose a linear connection on E and a positive definite metric. And then what happens is that I get this E connection on E. And now by the linear connection, I get this E connection on E. And now by the positive definite metric, I just construct another connection as the adjoint using that metric. Then we can construct these Chern-Simons transgression forms. And what happens is that we already seen it, that when K is odd, the trace of the curvature of this connection is equal to 0. And what happens for this adjoint connection with the metric is the same, that for K odd, the primary characteristic classes are 0. Therefore, we can construct these secondary characteristic classes. And our theorem, our result, is that these classes are independent of the choices that we make. So the linear connection and the positive definite metric are not relevant. So these classes are completely independent. And we call it the intrinsic secondary characteristic classes of a current algebroid. So just to finish, I want to say that we've seen it that for the standard current algebroid, or even for the twisted current algebroid, these secondary characteristic classes are 0. And the first class is the modular class that we define it. So these classes are appearing on degree 1, 5, 9. So in degree 1 is 0. And then we are not aware right now of any current algebroid that have non-vanishing secondary characteristic classes, but we believe that some examples can be built. Well, that's all that I want to talk. Thank you very much.
Thank you very much. Let's thank Michael for his talk, including emoji. Emoji applause, please, everyone. Emoji applause. Very good. Okay. So yeah, so we let's move on to our last speaker, not just of this session, but
the whole
of the whole conference. Yes. Francis, so I'm going to make you a co-host. So now you should be able to share slides, and I'm going to mute you as well.
Could you actually, I have my tablet also.
Oh, yeah.
Yep.
Yes, I see you. Okay.
Almost.
Yes.
So,
yeah, as I was saying at the beginning, it's mixed emotions. Very happy that we're nearing the end because we're all tired, but also kind of sad because this has been very, very exciting for us as organizers, I think.
Yeah, I completely agree, and I also think that it's a good outcome in sense of emotions. I would not like to have different.
Yes. So after the parallel sessions, I remind you there's still and in particular, I think one of the game rooms is probably going to be replaced with what is very quickly becoming the official board game of Junior Global Poisson, which is Code Names. So
yeah. Also, if you have other suggestions, if you want to do something particular, you can write us in Slack or anywhere else, and we can open another room. Yeah.
Yeah, and maybe last thing we mention is, so you know, a lot of the things that we kind of incorporated into this conference have been very much on a kind of experimental basis, and some of it worked, some of it maybe not quite. I mean, we already have basically a long list of things that we've learned, and we will modify. But surely there's, probably you might have suggestions and thoughts, and if you were organizing it, maybe you would have done something differently, and we would love to hear. If you want to share your ideas with us, it would be amazing.
I think maybe tomorrow we're going to send you a form with like feedback, and we will really appreciate if you fill it in.
Yeah.
Especially we appreciate the constructive criticism. Like
yes.
if there was something that you really wanted to be in this conference and you didn't find it here, yeah, or something that worked not quite not quite as expected, and yeah, so we'll really appreciate it.
Okay, I think we can well start whenever you're ready.
Okay, and the last speaker for our conference is Francis Bischoff, who talk about Lie groupoids and logarithmic connections.
Okay, thanks. Yeah, so I want to start by thanking the organizers, well, both for inviting me to speak, but also for putting on this this conference, which I think was really well done. So maybe everyone could join me in clicking your emojis. Okay, so let me just start. Okay. Okay, so I want to talk about this project, which I've just finished. I'll be putting up a paper on the archive soon. It's about Lie groupoids and logarithmic connections. So what I want to talk about is the study of flat connections with logarithmic singularities, and but using the tools from the theory of Lie groupoids to do this. So let me just start with some setting up what I'm going to be talking about. So I want to fix a complex reductive group G, and if you want, you can fix an example like GLN. And then in this talk, I'll be talking about connections on principal bundles. So I'll always denote these by P, and it will be over a manifold M, and then at some point it will change to X for some reason. Okay, so I want to start with kind of a warm-up, which is the classical Riemann-Hilbert correspondence for smooth connections. So this is an equivalence of categories between the category of flat connections on a manifold M and the category of representations of the fundamental group of the manifold. And I want to start by explaining how this correspondence, it arises by combining two more basic but also much more general equivalences, which are Lie's second theorem and Morita equivalence. So I'm going to start by explaining this. Just to start by defining some things. So given a principal G bundle P, we can define the Atiyah algebroid, which I've denoted at P. And what this is you take the tangent bundle of the total space of the principal bundle and you take the quotient by G. So this is a vector bundle over M. And the sections of this vector bundle, you can think of these as vector fields on the total space of P, but which are invariant under the G action. Then we can define a flat connection as a representation of the tangent bundle of the manifold, meaning that it's a bundle map from the tangent bundle to the T algebroid, and it preserves the Lie bracket. So here, this is the Lie bracket of vector fields on M, and here it's the Lie bracket of vector fields on P, on the total space of the principal bundle. And the tangent bundle and the T algebroid, these are both examples of Lie algebroids. And so we can phrase flat connections just as a homomorphism of Lie algebroids. And as an analogy to keep in mind, a representation of a Lie algebra, here little g, is a homomorphism of Lie algebras into the general linear algebra. So here you should think of the a T algebroid of a principal bundle as playing the role of the general linear algebra. Okay, so these Lie algebroids have integrations. So the tangent bundle integrates to the fundamental groupoid. This is a Lie groupoid, and it consists of paths in the manifold M taken up to homotopy. So here I have a picture. The T algebroid, it integrates to something that's called the gauge groupoid. This is also a groupoid over M, and the arrows in this groupoid correspond to isomorphisms between the fibers of the principal bundle, G-equivariant isomorphisms. So here, these are supposed to be kind of fibers of the principal bundle, and these are the arrows of the groupoid. They're maps between the fibers. Okay, so now we can define a representation of the fundamental groupoid on a principal bundle. This is a Lie groupoid homomorphism from the fundamental groupoid into the gauge groupoid of a principal bundle. So I drew a picture here. I'm imagining downstairs we have some paths, gamma 1 and gamma 2, and we're sending them to maps between the corresponding fibers. So phi of, say, gamma 1 is going from the fiber at the starting point of gamma to the fiber at the ending point of gamma. And again, the analogy to keep in mind is a representation of a Lie group as a homomorphism from a Lie group into a general linear group. And again, here, this gauge groupoid is playing the role of the general linear group. And a lot of things go through with this analogy. In particular, you have Lie's second theorem for Lie groupoid. So if you have a Lie groupoid G that has some connectivity assumptions on the source fibers, and its Lie algebroid is A, then we get an equivalence of categories between the representations of the algebroid and the representations of the groupoid. And this generalizes Lie's second theorem that you know for Lie groups and Lie algebras. And if we apply this to the case that we're studying, you get the first part of the Riemann-Hilbert correspondence. So we get to the equivalence between flat connections and representations of the fundamental groupoid. And the kind of the map going from a flat connection to a representation, just what you're probably familiar with. If you have a path on the manifold M and you have your flat connection, then in order to get the corresponding isomorphism between the fibers over the starting point and over the ending point, you use the connection and you solve a parallel transport equation, and it allows you to drag the fiber over the starting point to the fiber over the ending point. Okay, so this is the first part of the equivalence. The second part of the equivalence comes from something that's called Morita equivalence. So the fundamental groupoid of a manifold and its fundamental group at a base point, these are Morita equivalent groupoids. And what this means roughly is that if we take the quotient spaces of the base space modulo the groupoid, these things are the same. And there's a way of thinking of representations of a groupoid as a model for principal bundles over the quotient. So because these two quotients are the same, the fundamental groupoid and the fundamental group should have equivalent categories of representations. So this is the general fact about Morita equivalence, which is that Morita equivalence between two Lie groupoids, it induces an equivalence of categories between their categories of representations. So if we apply it to this case, we get the second part, of the Riemann-Hilbert correspondence, which is the equivalence between the representations of the fundamental groupoid and the representations of the fundamental group. Okay, so that's how we can see the Riemann-Hilbert correspondence for smooth connections. Okay, so now I want to move on to the main subject of the talk, which are logarithmic flat connections. So logarithmic flat connections, these are kind of the differential geometric generalization of linear ordinary differential equations with Fuchsian singularities. So here I've written down a kind of a prototypical example, and the presence of this z here, this means that the differential equation has a first order singularity. So the study of these types of differential equations, it goes way back, at least as far as Riemann and Fuchs. And there's a huge literature containing a whole bunch of normal form results, classification results. So I've listed a whole bunch of authors in the literature that have results about these equations. But one thing which I think is maybe missing is a completely functorial Riemann-Hilbert correspondence, kind of analogous to the one that I just presented for smooth connections, given in terms of monodromy data. So this is what I want to explain now. And this will go along the same, kind of following the same story as what I just presented for smooth connections. So to start, let me give kind of a Lie theoretic definition of logarithmic connections. So I want to fix now a complex manifold X and a smooth hypersurface D in this manifold. Associated to this data is the so-called logarithmic tangent bundle, which I wrote here as Tx minus log D. This is a Lie algebroid over X, and the sections of this Lie algebroid are vector fields on X that are tangent to D. Now we can define a flat connection with logarithmic singularities along D to be a Lie algebroid homomorphism now from this logarithmic tangent bundle into the T algebroid of a principal bundle. So this is completely analogous to the definition that I gave before. The only difference is that now we've replaced the tangent bundle with this logarithmic tangent bundle. And now that this is phrased in terms of Lie algebroids, the first part of the Riemann-Hilbert correspondence is straightforward. It's just Lie's second theorem. So the first step is the integration. So the logarithmic tangent bundle has an integration, which is the twisted fundamental groupoid. And so if we apply Lie's second theorem here, then we get an equivalence between the category of logarithmic flat connections and the category of representations of this twisted fundamental groupoid. So this is the first part of the Riemann-Hilbert correspondence. So now we'd like to understand this category here a bit better. And so to do this, we want to kind of replace the twisted fundamental groupoid with something which is easier to understand, but which is Morita equivalent to it. So this is kind of the Morita equivalent step. And the groupoid that we're going to use here is a groupoid that is, which I'm calling the groupoid of paths with tangential base points. So this is a groupoid N, and it's a groupoid over this union of a base point X naught in X and a fiber of the normal bundle to D. And what this, the way that you can think of this groupoid is that the arrows of this groupoid are paths in X, and they can have base points in X. So for example, here we have a path that has a base point at X naught, but we're also able to have base points that are not in the space X itself, but are in the normal bundle to D. So here in purple, this is supposed to be the normal bundle to this hypersurface D. So we're imagining that the paths can actually go from a point in X to a point in the normal bundle. So this was an idea originally due to Deling, and it's actually possible to make sense of this as a Lie groupoid. And this Lie groupoid is Morita equivalent to the twisted fundamental groupoid. And so we get an equivalence of categories. between the representations of the twisted fundamental groupoid and the representations of this new groupoid N. Okay, so now to understand this category of representations now, I want to kind of decompose N into some more simple building blocks. So to this end, I want to consider subgroupoids, some specific subgroupoids inside of N. So the first, for the first subgroupoid, I want to fix a tangential base point, namely a non-zero normal vector V, and I want to consider the subgroupoid, which consists of only paths that are allowed to go between this fixed tangential base point V and this fixed base point X naught. So for example, this path here is allowed, this path here is allowed, this path here is allowed, but you're not allowed to go to any other point in the normal bundle. So this is a discrete subgroupoid, and it's Morita equivalent to the fundamental group of X minus D. So that's the first subgroupoid. The second subgroupoid, which I've denoted A and XD, it consists of the paths that lie fully in the normal bundle. So these paths are not allowed to exit the normal bundle and move around in X. So this is another subgroupoid, and I'm not going to tell you exactly what it is. If you want to know, I can tell you in the parallel session, but the kind of essential thing is that it essentially boils down to an action groupoid associated to a multiplication action of scalars on the fiber of the normal bundle. Okay, so these are the two kind of building blocks, and the result, the first result is a sort of a Van Kampen theorem, which says that the groupoid N is completely built up out of these two building blocks. So it's a push out of Lie groupoids. And what this means is that if you want to understand the representations of N, all you need to do is understand the representations of these two subgroupoids. And so that means that to study the representations, it basically boils down to studying the representations of the fundamental group of the complement, which is straightforward, we know how to do that, and then the representations of an action groupoid of complex numbers acting on a one-dimensional vector space. So for the rest, well, most of the remainder of the talk, I want to just zero in on this groupoid. Okay, so just to make contact with differential equations again, the representations of this groupoid are equivalent to linear ordinary differential equations with Fuchsian singularities. So differential equations of this form. So really, when we're studying representations of this action groupoid, it's the same thing as studying the connections kind of locally. So we're just studying a differential equation now. So let me start by saying a bit about this groupoid. So this is a groupoid, an action groupoid associated to the exponentiated action of C. The arrows, they consist of a point lambda in C and a point Z in the affine line A. And we think of these as arrows going from Z to e to the lambda times Z. This groupoid has two orbits. One of them is the point 0, because multiplication by a scalar can't move you away from 0. And the other orbit is this big open orbit, which is the complement of 0. Now, it's useful to look at the isotropy groups. So these are the groups consisting of arrows that start and end at the same base point. Over the point 0, because the action of C can't move you away, you get the entire copy of C over the point 0. Over a point in the open orbit, for example, 1, we just get Z. So this is the fundamental group of the complement of the point 0 and A. So the elements of Z, you can think of them as these kind of loops going around. Okay, so now if we have a representation phi, we can extract some invariance from the representation in order to classify it. So recall again, I'm thinking of a representation as a homomorphism from our groupoid into the gauge groupoid of a principal bundle. And the first invariants that we can extract, they come from looking at the isotropy groups. So if we look at the isotropy group over the point 1, we get the monodromy. So this is an automorphism of the fiber over 1. And it comes about by looking at the action of the loops going around the point 0. That's the monodromy. the residue of a representation, this comes by looking at the action of the isotropy group over the point 0. So this gives you an action of C. And so the residue can be thought of as an infinitesimal automorphism acting on the fiber over the point 0. Okay, so these are the invariants that we can get from the isotropy groups. We basically need only one more invariant to classify representations. And this has to do with connecting the fiber over 0 and the fiber over 1. So this last thing is a space of regularized parallel transport maps. So I'm going to say more about this in a minute, but these three things are what classify representations of this action groupoid. So you can think of them as generalized monodromy data as in the following picture. And these things, we can kind of organize them into a category, and then we can get an equivalence of categories between the representations of the action groupoid and this category of generalized monodromy data. Okay, so now I want to talk about the spaces of regularized parallel transports. So the way I'm going to describe this will require a couple of definitions. The first one is the definition of a linear approximation of a representation. And the easiest way I find of thinking about this is to think about the following kind of natural groupoid homomorphism, where you just project out the second point, you send it to 0. So this is a groupoid homomorphism from the action groupoid to itself. And by pullback, we get a functor from the category of representations to itself. And what it does is it takes an arbitrary representation and it outputs the trivial representation, which is determined by the residue. So here we're starting with P phi, and we apply the functor L, and we get this linear approximation of the representation. So it's on a trivial bundle where the fiber now is the fiber of the original connection or representation at the point 0. Okay, so this is the linear approximation. And now the kind of important definition is the notion of a linearization. So a linearization of a representation is an isomorphism, which goes from the linear approximation of a representation to the representation itself. And if we put the extra condition that this map T has to be the identity at the point 0, then the linearization is said to be strict. And so linearizations, these can be thought of as providing a regularized parallel transport. One way of seeing this is the map T, if we say evaluate it at the point 1, then it's a bundle map. It's going from the fiber over the point 0 to the fiber over the point 1. So it's really connecting it's relating the fibers over the two orbits. And these linearizations, these encode the asymptotic nature of the fundamental solutions at the singularity of the associated differential equation. So they're closely related to something which is called the Levelt filtration. Okay, so there's one complication in the story, which is that linearizations are not guaranteed to exist. And this is because of the phenomenon of resonance. And resonance is basically the main source of subtlety in understanding these types of differential equations. So resonance obstructs the existence of linearizations. But the interesting thing actually is that it's not just resonance, it has to do with the unipotent component of the monodromy. So if you have a representation where the monodromy is semi-simple or diagonalizable, then you're guaranteed the existence of linearizations. So the way to circumvent the problem that linearizations don't exist is to use the semi-simple part. So I want to explain how we can use a Jordan-Chevalier decomposition to decompose a representation into a semi-simple and unipotent component. So this is the content of the following theorem. We start with a given representation, P phi, and what we can do using this formula, which I can explain later, is we cook up a groupoid 1 cocycle. And the only important thing to know about a groupoid cocycle is it's something that allows you to deform a representation. So we take this cocycle and we use it to deform our representation. And we get a new representation that has semi-simple monodromy. So this defines a functorial Jordan-Chevalier decomposition for representations. And basically, this is the way that we define the space of regularized parallel transports. We define these to be the space of strict linearizations of the semi-simple component of a representation. Okay, so this is all I want to say about the representations of this action groupoid. I want to now kind of zoom out again and go back to the general case. So just to recap, we saw that we start with a manifold X with a hypersurface D, and we're studying the category of logarithmic connections, flat connections, and using Lee's second theorem and Morita equivalence, we've gotten an equivalence between this category and a category of representations of a groupoid N. And we saw that this groupoid N can be thought of as a groupoid of paths in X, but which have tangential base points on the normal bundle to the hypersurface. And then we saw that this groupoid, it decomposes into these simple building blocks, which consists of the fundamental group of X minus D and then this action groupoid. And then we've just studied how do we classify representations of this action groupoid. Okay, so now we can just put everything together. And this will kind of combine, we put all the pieces together and it will give us a functorial Riemann-Hilbert correspondence for logarithmic connections in terms of generalized monodromy data. So in order to do this, we need to define a category of generalized parallel transport. I can describe this more in the parallel session, but it basically consists of the data of a representation of X minus D, and then over the divisor, we get these infinitesimal residue symmetries, and then connecting the points over D, and then the point X naught. In the complement, we have the space of regularized parallel transports. So we get this kind of category that contains these regularized, or these generalized monodromy type data. Okay, and then the result then is that we get an explicit equivalence of categories, which goes between the category of flat connections on X with logarithmic singularities along D and the category of generalized monodromy data. And I want to stress that this equivalence of categories, it's really given by a pair of two functors that you can write down explicitly. So you have kind of an explicit recipe for going back and forth between the connections and the monodromy data. Okay, so that's the end. Thanks.
Thank you very much, Francis, for a wonderful talk. Let's all give a round of applause to Francis, including emoji applause. Everyone, emoji applause. Okay, thank you.
Thank you, Francis.
Sorry?
No, I was saying thank you, Francis.
Yes, thank you, Francis. Yeah. So okay, so now so we should take like a 10-minute break, especially the speakers a few minutes to stretch their legs, and we are continuing on to the parallel session. So to remind, all the 4 speakers are split into 4 rooms. So Cedric is in room 1, Tobias is in room 2, Michael is in room 3, and Francis is in room 4.
The rooms are already open.
The rooms are
1 and 2 are already open.
And 3 and 4 are being
will be open
as we
in
speak.
a few seconds.
Yes.
Yeah.
Yeah.
Okay, so by this we're
finishing
the common events on the conference.
Yes. Thank you very much.
Still hope to see you on the parallel session and on social part. Thank you very much for attending.
Thanks a lot.
Yeah, I'd really like to thank Nikita and Beatrice for being wonderful co-organizers and making all of this happen.
Thank you, and I want to thank Nesta, who's an amazing co-organizer. Yeah, thanks, thanks a lot. I didn't expect this to degenerate into a thanking session. Anyway, yeah, let's we'll see each other at parallel sessions. So see you all.
Yeah, see you.
Okay, well, this was good.